You will never, in your entire life, travel 1 light year. And that's if we left today with the best technology we've ever built. So the real question isn't whether the journey is possible. It's whether anything alive when we launch would still be alive when we arrive. Because 1 light year isn't just a distance. It's generations. It's people born on a ship who will never know Earth, growing old in the dark between 2 stars. And when they finally arrive, will they even remember why they left? If questions like this one stir something in you, make sure to give this video a like. Now let's get started. You've probably heard that a light year is a unit of distance, not time. But here's the problem. Your brain hears light year and files it somewhere next to really, really far and then moves on. That's not good enough for what we're about to discuss. So let's try a different approach. Picture a grain of sand. Hold it in your mind, small, pale, barely visible. Now imagine placing that single grain on the center of a large football pitch. That grain of sand represents our solar system, everything. The sun, all 8 planets, the asteroid belt, the dwarf planets, the scattered disk objects at the edge of our planetary neighborhood. All of it compressed into 1 grain of sand on a football field. The football pitch itself? That's roughly the scale of 1 light year. Everything humanity has ever physically reached, every probe we've ever launched, every signal we've ever sent, contained in a grain of sand inside a football pitch representing just 1 light year of space. Now here's where it builds. The nearest star system to us, a gravitationally bound trio of stars that most people have never thought about in any real detail, sits about 4.2 light years away. So picture 4 of those football pitches lined up end to end. Our grain of sand sits at one end. That's the journey to the nearest neighbors, not the journey across the galaxy, not to another galaxy, just to the nearest stars. 4 pitches, and we haven't even left our cosmic street. Sirius, the brightest star you can see in the night sky from most of the planet, is about 8.6 light years away, roughly 8.5 football pitches. Betelgeuse, that reddish, brooding giant in the shoulder of Orion that ancient civilizations used to navigate by, sits somewhere around 700 light years from where you're sitting right now. The center of our own Milky Way galaxy is 26,000 light years away, and the observable universe, the full sphere of space we can currently detect with our best instruments, stretches approximately 93 billion light years across. So when we ask what happens if we travel 1 light year, we are not asking about reaching another star, we're asking about a journey through the space between stars, through the vast, ancient quiet that separates one solar system from another. 1 light year gets us out of our immediate neighborhood, past the outermost shell of material that our sun has gravitational influence over, into something called the interstellar medium. And the interstellar medium is not what most people think it is. Most people imagine space as empty, a vacuum, nothing. And in the technical sense, yes, it's far closer to a perfect vacuum than anything we can create in a laboratory on Earth. But empty is the wrong word. It's actually filled with something, thin, ancient, and in certain ways, deeply strange. The interstellar medium is a diffuse mixture of gas, mostly hydrogen and helium, along with dust, cosmic rays, magnetic fields, and the faint remnant glow of stars that died long before our sun was even born. It has structure, it has temperature variations, it has regions that are hot, regions that are cold, and giant molecular clouds so dense and dark that they block out entire fields of stars behind them. And here's the part most space travel videos skip entirely, that interstellar medium is not a neutral environment. For any object moving through it at serious speed, it becomes a threat. Not in the way that asteroids are a threat, in a subtler, stranger, and arguably harder to solve way. We'll come back to that. But first, let's ground ourselves in what's actually realistic, because this is where the video stops being poetic and starts being honest. If a mission launched in 2026 using the best propulsion technology currently available, or anything we could plausibly develop within the next few years, what are we actually working with? Let's begin with chemical propulsion. The technology that took us to the moon, the technology that has flung robotic probes into the outer solar system and beyond. The fastest sustained velocities achieved using chemical rockets combined with gravitational assists from planets puts objects at roughly 40,000 to 60,000 kilometers per hour relative to the Sun. Let's be generous. Let's say we launch something or someone at a clean, sustained 50,000 kilometers per hour. 1 light-year is 9.46 trillion kilometers. At 50,000 kilometers per hour, traveling that distance would take approximately 21,000 years. 21,000 years. Sit with that for a moment. 21,000 years ago, our ancestors were living through the last great ice age. Agriculture didn't exist, cities didn't exist, writing didn't exist. Humanity was painting ochre animals onto cave walls and following herds across frozen tundra. In 21,000 years from now, if the entire arc of what we call recorded civilization were to happen again, twice, a chemical rocket launched today at its very best speed would still not have crossed 1 light-year of space. Chemical propulsion isn't just impractical for this kind of journey. It's categorically, fundamentally, mathematically impossible for anything resembling a crewed mission to another star. So what's next? Nuclear thermal propulsion. And this is not science fiction. This is an active area of development. NASA and DARPA have been jointly working on a program called DRACO, the demonstration rocket for agile cislunar operations. The concept is elegant in a brutal sort of way. Instead of burning chemical fuel to generate heat and thrust, you run hydrogen propellant through a nuclear reactor. The reactor heats the hydrogen to extreme temperatures, and the gas expands and fires out the back at incredible velocity. The result is roughly double the efficiency, what engineers call specific impulse, of the best chemical engines we currently possess. With nuclear thermal propulsion, theoretical top speeds for a deep space mission could reach somewhere around 90,000 kilometers per hour. At 90,000 kilometers per hour, 1 light-year would take approximately 12,000 years. Better, genuinely better. But 12,000 years is still longer than all of recorded human history, by a wide margin, and at this point, we haven't even started talking about what the journey would actually do to the people on board, or what they would eat, or how they would breathe, or what happens to the human skeleton after years of microgravity and high-energy radiation pouring through the ship from every direction. These are not secondary concerns. They are the wall that every serious conversation about interstellar travel eventually runs into. But here's what's interesting. Here's what I haven't told you yet. And this is the piece of the story that actually matters, the part that separates a depressing set of math problems from something genuinely exciting. There is a propulsion concept, a real one, grounded in physics we already understand, studied seriously at real research institutions, not dreamed up for a movie. A concept that could, in theory, reduce that 21,000-year chemical rocket journey to something a human being might actually be able to survive. Something that could change the entire equation of what interstellar travel means. It's not a warp drive, it's not a wormhole, it's not anything that requires us to rewrite physics. It's built on ideas that have been sitting in scientific literature for decades, waiting for the engineering to catch up. Stay with me, because this is where it stops being abstract and starts being something you can almost touch. Tonight, if the sky is clear where you are, I want you to go outside, not to take a photo, not to pull up an app, just to look, to let your eyes adjust to the dark and let the universe actually land on you the way it did for every human being who ever lived before electric light swallowed the night. And if you've ever stood there, then I want to mention something quietly, because I think it genuinely matters. There is a telescope called the Celestron Starsense Explorer, and the reason I bring it up, it's because of what it does to a person the first time they actually see Saturn's rings with their own eyes, or trace the edge of a nebula, or resolve what looked like a smudge of light into a cluster of ancient, dying stars. That experience changes something in you in a way that no video can fully replicate. The Starsense Explorer uses your phone's camera to map the sky automatically, which means you don't need any prior experience. You don't need to know where anything is. You just point, and it finds the universe for you. If you're curious, the link is in the description and pinned on the comments. The idea has a name that sounds almost too simple for what it proposes: a solar sail, or more precisely, a laser-driven light sail. And before your mind goes to anything resembling a children's science exhibit, let me tell you what this actually involves at the serious research level, because the physics here is real, the engineering is being actively developed, and the implications are, in the most literal sense of the word, astronomical. Light carries momentum. This is not a poetic metaphor. This is measured, verified, experimentally confirmed physics. When a photon, a particle of light, strikes a surface and reflects off it, it transfers a tiny amount of momentum to that surface. Tiny, unimaginably tiny on the scale of everyday objects. But in the vacuum of space, where there is no air resistance, no friction, no gravitational drag from a nearby planet, even the smallest sustained force accumulates. And if you replace sunlight with a focused, ground-based laser array of sufficient power, aimed at a reflective sail, thin enough to be measured in atoms rather than millimeters, the acceleration becomes genuinely significant. This is the core of the Breakthrough Starshot initiative, announced in 2016 by a group of serious scientists and researchers, including the late Stephen Hawking. Breakthrough Starshot proposed sending a fleet of gram-scale probes, each attached to a sail just a few meters across, and accelerating them using a laser array with a combined output of roughly 100 gigawatts. At those energy levels, the tiny probes could theoretically reach approximately 20% of the speed of light. 20% of the speed of light. That's roughly 60 million kilometers per hour. At that velocity, 1 light year would take approximately 5 years. 5 years, not 12,000, not 21,000, 5. Now, and this is the part where intellectual honesty demands we slow down and be very precise. The Breakthrough Starshot proposal in its current form is designed for gram-scale robotic probes. Wafer-thin, chip-sized spacecraft carrying miniaturized sensors and a laser communication system. Not human beings, not a crewed vessel. The laser array required doesn't exist yet. The sail materials required don't fully exist yet. The pointing accuracy required, keeping a laser beam precisely on a sail, moving at relativistic speeds across interstellar distances, is an engineering challenge of staggering proportions. But the physics works, the equations hold, and the research continues. So what does this mean for the 2026 question? It means that if we're being honest, a crewed mission to 1 light year is not something that can happen in 2026 or in 2050 or possibly in this century at all, but a probe, a robotic emissary, using laser propulsion derived from the Starshot concept. That conversation is genuinely closer than most people realize. The engineering gaps are real, but they are not gaps that require new physics. They require materials science, sustained funding, and international cooperation, all of which are hard, none of which are impossible. And that distinction between impossible and not yet is one of the most important things science has ever taught humanity. But let's do something more interesting now. Let's actually go, not in a probe, not in an abstraction. Let's imagine that, through some combination of engineering genius, political will, and generations of dedication, Humanity builds a crude vessel capable of reaching and maintaining a speed of about 1% of the speed of light. That's approximately 3 million kilometers per hour. Aggressive, optimistic, but within the outer boundary of what certain serious proposals, like nuclear pulse propulsion, suggest might eventually be achievable. At 1% of the speed of light, crossing 1 light-year takes 100 years, a century. Long, yes, but a number a human mind can actually hold. Long enough to require multiple generations of crew, what scientists and theorists call a generation ship, but short enough that the civilization that launched the mission in 2026 would still exist, still be transmitting, still be waiting on the other end of a signal that takes 1 year to arrive. So launch day 2026, you leave. What does departure actually look like from inside? In the first hours and days, everything is still familiar. Earth is a visible disk behind you, growing smaller but still recognizable. The blue, the white cloud systems, the subtle brown and green of continents. The moon slides past, a scarred grey world that humans walked on in 1969 and haven't physically returned to since, though that will likely change before any interstellar departure could ever be attempted. The sun ahead, no, behind you now, still blazes with familiar intensity. Solar wind particles stream past the hull. The radio signals from Earth arrive clearly, almost in real time, with only seconds of delay. In the first weeks, Mars might be visible, depending on its orbital position. The asteroid belt, which almost no one pictures correctly as a sparse field of tumbling rocks spread across an immense volume of space rather than the dense obstacle course movies suggest, passes without drama. The rocks are hundreds of thousands of kilometers apart on average. You don't dodge them, you barely notice them. In the first months, Jupiter rises into view. Let me give you a sense of what that means. Jupiter is the largest planet in our solar system by an enormous margin. Its diameter is about 140,000 kilometers, roughly 11 times Earth's. The Great Red Spot, a storm that has been raging for at least 350 years, is itself larger than our entire planet. As your vessel passes at distance, Jupiter becomes the largest single thing you have ever seen in space outside the Sun itself. Its 4 largest moons in Io, Europa, Ganymede, and Callisto, are visible as distinct worlds, not points of light. Europa in particular might catch your eye. Beneath that fractured, ice-covered surface lies an ocean of liquid water, an ocean that has been sitting there in the dark, warmed by the gravitational flexing of Jupiter's immense gravity for billions of years. Whether anything lives in that ocean is one of the most profound open questions in the whole of science. And you're passing by it on your way out. Saturn comes into view several months later, and here is where something shifts. Something subtle but important. Saturn's rings, that impossible, geometry-defying structure of ice and rock and dust, stretched across hundreds of thousands of kilometers, look different when you're not looking at them from Earth, through an atmosphere and a telescope. From space, from proximity, they are not a single flat disk. They have structure, gaps, waves, textures. The Cassini division, a gap in the rings named after the 17th century astronomer Giovanni Cassini, is wide enough to fit our entire moon inside it. The rings themselves are extraordinarily thin relative to their width. If you scaled Saturn's rings down to the size of a sheet of paper, that paper would be wider than a football pitch. From a distance, they look solid. Up close, they are individual particles, each orbiting Saturn in its own precise path, collectively creating the illusion of something whole. Then Saturn is behind you as well, Uranus, Neptune, both pale blue. Uranus from methane in its upper atmosphere, Neptune from a slightly different methane composition, combined with an unknown absorber that scientists are still debating. Neptune is so far from the Sun that sunlight reaching it is 900 times dimmer than what falls on Earth. It should be a cold, dark, silent world. Instead, it has winds reaching 2,100 kilometers per hour, the fastest in the solar system. A place we have visited exactly once with Voyager 2 in 1989 and have not been back to since. There are missions being planned, proposals being written. The ice giants are arguably the least understood major category of planet in our solar system, and they sit right here in our own backyard, patiently waiting. Past Neptune, you enter a region called the Kuiper Belt. This is where things start feeling genuinely different. The Kuiper Belt is a disk of icy objects extending from roughly 30 astronomical units, 30 times the distance from Earth to the Sun, out to about 50 astronomical units. Pluto lives here. So does Eris, Makemake, Haumea, and thousands of smaller bodies we haven't even named yet. New Horizons, the probe that gave us our first close images of Pluto in 2015, found a world of unexpected geological complexity, mountains of water ice, a vast nitrogen plain, a hazy layered atmosphere. A world we had written off as a cold, dead rock turned out to have a personality. At 1% of the speed of light, the Kuiper Belt passes in a matter of months, but as you clear its outer edge, something changes that no instrument fully prepares you for. The sun becomes a star, not a disk. Not a blazing presence that you have to shield your eyes from, a very bright star, the brightest in the sky by far, but a star, a point of light. And with that visual shift comes something existential that is difficult to put into words, because for the entirety of human existence, for every culture, every civilization, every human being that has ever breathed air on Earth, the sun has been a presence. A large, daily, warm, governing presence. The thing that defines morning and evening, that determines seasons, that photosynthesis runs on, that all life on this planet ultimately depends on. To see it become a star, to watch it shrink from a disk into a point, is to cross a psychological threshold that might be one of the most profound experiences a human being could ever have. And you haven't even reached the edge of the solar system yet. There is a boundary at the edge of our solar system that no human being has ever crossed. No crewed vessel has ever approached it. Only 2 objects made by human hands have passed through it, and both of them did so without cameras, without the ability to turn around and take a photograph, without any way to transmit the kind of data that would let us truly visualize what that crossing looks like from the inside. That boundary is called the heliopause, and it is one of the most extraordinary, least discussed structures in the entire solar system. Here is what it is precisely. The sun is constantly exhaling, not metaphorically, literally. A continuous stream of charged particles, mostly protons and electrons, flows outward from the sun in every direction at speeds of roughly 400 to 800 kilometers per second. This is the solar wind. It fills the entire solar system, pressing outward against the interstellar medium, that thin ancient gas and dust filling the space between stars in a constant dynamic struggle. The bubble created by this outward pressure is called the heliosphere, and the heliopause is where the solar wind finally runs out of energy, where it slows, stalls, and is pushed back by the pressure of interstellar space. Where the sun's breath meets the rest of the galaxy. Voyager 1 crossed the heliopause in 2012. Voyager 2 followed in 2018. The data they sent back was startling in ways that are still being analyzed. The boundary is not a clean spherical shell, it's asymmetrical, compressed on one side by the motion of our solar system through the galaxy, elongated into a long tail on the other. It has fine structure, ripples and fluctuations driven by variations in the solar wind and changes in the surrounding interstellar medium, and the transition from inside to outside is not instantaneous. It's a zone, a region of turbulence and mixing that takes time and distance to fully resolve. Based on Voyager data, the heliopause sits roughly 120 astronomical units from the Sun. 1 astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. So the heliopause is approximately 18 billion kilometers from where you started. At 1% of the speed of light, 3 million kilometers per hour, your vessel crosses this distance in roughly 250 days, less than a year after departure, less than a year, and already you are somewhere no human being has ever been. The moment of crossing is not dramatic in the way that space crossings tend to be portrayed. There is no visible wall, no flash of light, no sudden change in the view outside the window. But the instruments notice immediately the solar wind particles that have been streaming past your hull since departure. The constant, measurable flow of charged particles from the sun drops sharply in intensity. The magnetic field around the ship shifts. The orientation of the field lines changes because interstellar magnetic fields run at a different angle to the fields within the heliosphere. The background radiation environment changes as well. Inside the heliosphere, the solar wind partially shields the inner solar system from galactic cosmic rays, high-energy particles accelerated by distant supernovae and other violent events across the galaxy, traveling at nearly the speed of light in some cases. The sun's magnetic bubble deflects a portion of these. Outside the heliopause, that protection is gone. Galactic cosmic rays become one of the most serious long-term threats to both the crew and the ship's electronics. These are not the kind of radiation you can simply shield against with a thick wall. High-energy cosmic rays pass through matter, interacting with the nuclei of atoms in the shielding material and producing secondary cascades of particles that can, in some cases, be more damaging than the original radiation. This is a problem that no currently existing shielding technology fully solves. Water is actually one of the better absorbers, and some proposals for crewed interstellar vessels suggest surrounding the habitation module with tanks of water or liquid hydrogen for exactly this reason. But there is no perfect solution. The crew of any interstellar vessel would be accepting a meaningfully elevated lifetime radiation dose. That's not speculation. That's physics beyond the heliopause. Something else changes. Something more personal, more psychological. You are now in the interstellar medium, and the solar system behind you is shrinking into something new. The sun is still the brightest star in the sky by a significant margin. Even from 120 astronomical units, it outshines everything else. But it is no longer the sun in the way any human being has ever experienced it. It is a very bright star in a sky full of stars. And all those other stars, the ones that have always been fixed, background lights, they haven't moved, because at 120 astronomical units, you've barely begun. 1 light year is over 63,000 astronomical units. You are not yet 0.2% of the way there. The interstellar medium that surrounds you now is not the comfortable solar wind-swept environment of the inner solar system. It is something older, something that was here long before the sun was born. The gas filling this region, diffuse, cold, ancient, is mostly hydrogen, with significant helium and trace amounts of heavier elements forged in the cores and deaths of stars that lived and died billions of years before our sun ignited. The dust grains suspended in it are complex, carbon-rich structures, some of them possibly carrying organic molecules. This is not empty space. It is, in a very real sense, the raw material of future stars and planets, drifting in slow ancient suspension. And here is something that rarely gets mentioned in discussions of interstellar travel because it sounds counterintuitive. At genuinely high speeds, this thin medium becomes a hazard. At 1% of the speed of light, even a hydrogen atom, a single proton, becomes a radiation hazard when it impacts your hull. At that relative velocity, interstellar hydrogen impacts carry enough energy to cause damage at the atomic level over time, eroding the leading face of the ship through a process called interstellar erosion. The faster you go, the worse this gets. At the 20% of light speed proposed for breakthrough Starshot's tiny probes, the problem is severe enough that the sail design has to account for it explicitly. Proposed solutions include magnetic shielding, using a superconducting loop to generate a magnetic field that deflects charged particles around the ship, and physical nose cones of erosion-resistant materials. Neither solution is fully developed. Both are being researched. This is the texture of the problem. Not how do we go fast enough alone, but how do we survive going fast enough? And the two questions are deeply intertwined. Now let's talk about what you're traveling through in more detail, because the interstellar medium is not uniform. It has regions, structures, a geography, if you want to call it that. Our solar system currently sits inside what astronomers call the local bubble, a region of unusually hot, low-density interstellar gas stretching roughly 1,000 light-years across in several directions. The local bubble is thought to have been carved out by a series of supernova explosions, massive stars that died violently over the past 10 to 20 million years, blasting away the surrounding gas and dust and leaving behind a vast, hot, relatively empty cavity. We live inside this cavity. Our solar system has been drifting through it for millions of years. The local interstellar cloud, also called the local fluff, is a slightly denser region within the local bubble, and it is the specific parcel of interstellar gas our solar system is currently moving through. It's approximately 30 light-years across. The temperature inside it is roughly 6,000 degrees Celsius, hot in the technical sense, meaning the particles are moving very fast, but so sparse that this temperature would feel like nothing to a physical object passing through it. In the interstellar medium, temperature and density are almost completely decoupled from the way we experience them on Earth. 6,000 degrees in a near-perfect vacuum carries almost no thermal energy at all. Within the first light year of departure from Earth, your vessel stays well within this local interstellar cloud. The gas around you is hot, thin, and ancient. The stars ahead are distant, fixed, barely changing their apparent positions, even as you travel at speeds that would cross our entire planet in under 15 seconds. This is perhaps the most psychologically challenging aspect of interstellar travel that rarely gets addressed. The stars don't move, not perceptibly, not on the timescale of a human lifetime, at 1% of light speed. The sky ahead of you looks almost identical to the sky you left behind in terms of the star field. Individual stars shift their position by tiny fractions of a degree per year, a phenomenon called parallax. But it's not something the naked eye would easily detect without careful, repeated measurement. The universe at these scales does not cooperate with the human need to feel like progress is being made. This is one of the most serious psychological challenges for any long-duration deep space mission, and it's not hypothetical. NASA's Human Research Program has been studying isolation, confinement, and the psychological effects of long-duration spaceflight for decades. The studies conducted on the International Space Station, on analog missions in Antarctica, and in isolation chambers on Earth have all pointed to the same cluster of challenges: monotony, the loss of a sense of progress, interpersonal conflict in small groups, and what researchers call third-quarter phenomenon, a dip in morale and performance that tends to occur in the latter portion of any long, isolated mission. On a journey measured in decades or centuries, these dynamics become existential design challenges, not just crew welfare concerns. But here's something that genuinely surprises most people when they first encounter it. Something that turns the isolation from a purely negative force into something stranger and more interesting. As your vessel accelerates to 1% of the speed of light and sustains that velocity, the effects of special relativity begin, just barely, to apply. The time dilation at 1% of light speed is negligible. The Lorentz factor at that velocity is approximately 1.0005. For every 1,000 years that pass on Earth, the crew experiences 999 years and about 6.5 months, not exactly a dramatic time-saving measure, but push the velocity higher, toward 10% of light speed, and things start to shift. At 10%, the Lorentz factor is approximately 1.005. Still modest. At 50% of light speed, time dilation becomes genuinely significant, a factor of about 1.15. For every year the crew experiences, 1.15 years pass on Earth. And at 90% of light speed, the factor rises to about 2.3. For every year on the ship, 2.3 years pass back home. This means that the faster you go, the more the journey compresses for the travelers, while the universe outside continues aging at its usual pace. At truly relativistic speeds, 99% of light speed, the Lorentz factor is roughly 7. A journey of 1 light year takes about 1 year on the ship, but 7 years on Earth. At the theoretical extreme, 99.9% of light speed, the Lorentz factor approaches 22. A journey of 1 light year takes about 16 days on board, but 22 years for the civilization you left behind. The universe permits this. The universe has permitted this since its first moments. We are the ones who have only recently understood it clearly enough to even ask the question. Some are in year 3 of your departure, traveling at 1% of the speed of light. Something happens that is worth pausing on. You've covered roughly 0.03 light years, a tiny fraction. The sun behind you is now one of the brighter stars in the sky, but no longer obviously dominant. The constellation patterns around you have barely shifted. Earth, that pale blue point of light that you can no longer resolve as a disk without optical aid, is receiving radio signals you sent 3.5 weeks ago. Any reply from home takes 3.5 weeks to reach you. That communication lag is growing. Every week it grows a little more. And the psychological weight of that growing silence, of knowing that everything you say to the people you left behind takes longer and longer to reach them, and their replies take equally longer to reach you, is something no simulation, no analog mission, no Earth-based isolation study has ever truly replicated. There's a word in Portuguese, and I think of it often in contexts like this, saudade. It doesn't translate cleanly into English. It describes a deep, nostalgic longing for something or someone you love, but that is absent. For the crew of an interstellar vessel, saudade might be the most honest word for the emotional texture of the journey. Not grief, not sadness exactly, something more complex. A love for something that still exists but is increasingly, irreversibly, unreachably far away. And yet, and this is what I want to leave with you as we move deeper into this journey, there is something else growing alongside that longing. Something that every astronaut who has looked back at Earth from low orbit has described in some form. A perspective shift so profound it has its own name, the overview effect. The experience of seeing Earth from outside it, small, whole, brilliant and impossibly fragile, produces a reliable, documented change in how people understand their own lives, their conflicts, their priorities. Astronauts consistently report feeling that national borders, political disputes, and interpersonal conflicts look different, smaller, less urgent from outside the atmosphere. Now imagine that effect, amplified by 3 years of travel, by the sun becoming just another star, by the realization that you are moving through a space so vast that the word vast stops meaning anything useful. What does it do to a human being? What does it do to a community of human beings isolated together in a small vessel, moving through the ancient dark between stars? That question, the human one, the one about what this journey makes of us, is the one that gets me more than the physics. And it's the one we're going to dig into now, alongside something genuinely remarkable. what a vessel crossing the 1/4 light-year mark would actually be able to detect, observe, and measure about the galaxy around it that we simply cannot see from inside the solar system. The universe looks different from out there, and some of what it shows you changes the questions you thought you were asking. Let's talk about something that doesn't get nearly enough attention in conversations about interstellar travel, something that sits right at the intersection of biology, psychology, philosophy, and engineering, and that no amount of rocket science alone can solve. What happens to the people? Not the ship, not the propulsion system, not the radiation shielding or the food production or the recycled water systems, though all of those matter enormously. What happens to the human beings inside the vessel, their minds, their relationships, their sense of identity, their understanding of who they are and where they belong? Over decades of travel through a darkness so complete and so vast that every framework their species ever built for understanding the world slowly becomes inapplicable. This is not a soft question. It is not a philosophical indulgence. It is arguably the central engineering challenge of crewed interstellar travel, because a ship that works perfectly and carries a crew that has psychologically collapsed is not a successful mission. It is a tragedy moving at 3 million kilometers per hour through the dark. Let's begin with what we actually know. Not speculation, not science fiction extrapolation. What peer-reviewed research, long-duration spaceflight data, and isolation studies have actually told us about human beings in extreme confinement? The longest continuous spaceflight on record was completed by Russian cosmonaut Valery Polyakov, who spent 437 days aboard the Mir space station between 1994 and 1995. More recently, NASA astronaut Frank Rubio spent 371 days aboard the International Space Station, returning in September 2023 after his mission was extended due to a Soyuz capsule issue. Scott Kelly spent 340 days on the ISS as part of the landmark twin study, during which researchers compared his biology, cognition, and gene expression against his identical twin brother Mark Kelly, who remained on Earth. The findings were revelatory. Scott's telomeres, the protective caps on the ends of chromosomes, often used as a marker of cellular aging, actually lengthened during his time in space, which was unexpected. His gut microbiome shifted significantly. His cognitive performance showed measurable changes. His gene expression, which genes were active and which were suppressed, showed thousands of alterations compared to his brother on the ground, the vast majority of which returned to near baseline within months of his return. But some did not. Some changes persisted. Space changed his biology in ways that are still being analyzed and understood, and that was less than a year, in low Earth orbit, with regular communication with family and mission control, with resupply missions bringing fresh food and equipment, with the psychological anchor of knowing that Earth was right there, visible through the window, a few hundred kilometers below. Now imagine multiplying that duration by a factor of 100 or 1,000, because a journey to 1 light year at realistic speeds doesn't end in a year or 5 years. It ends in a century or more for a crewed vessel. And the Earth outside the window is not a few hundred kilometers below. It is years of signal delay away. A place that, by the time you arrive at your destination, will have changed in ways you cannot predict, cannot fully follow, and cannot return to in any meaningful time frame. The concept of a generation ship addresses the duration problem by reframing it entirely. Instead of asking, how do we keep one crew alive long enough to complete the journey, it asks a different question. How do we build a society that sustains itself across multiple generations, maintains the mission's purpose and integrity across centuries, and arrives at the destination with people who are capable, motivated, and psychologically equipped to do something useful when they get there. This reframing is fascinating because it turns a physics problem into a civilization problem. A generation ship is not just a spacecraft, it is a world, a closed, self-sustaining biosphere with food production, energy generation, waste recycling, medical facilities, social structures, governance systems, cultural institutions, education systems, and a mechanism for transmitting the mission's purpose across generations who did not choose to be there. That last point is the one philosophers and ethicists find most challenging. The people born on a generation ship, the second generation, the third, the fifth, never consented to the journey. They were born into it. They cannot leave. Their entire life, everything they will ever know or experience, is contained within the walls of a vessel moving through the dark. The closest analog we have in human history is perhaps the experience of people born into isolated island communities or into nomadic groups with limited contact with the outside world. But even those parallels break down quickly. No island community was physically separated from the rest of humanity by a growing gulf of light years. The philosopher and bioethicist Francine Rousseau has written extensively on what she calls the birth consent problem in generation ship ethics. The question is not just whether the mission is worthwhile, it's whether the people who run the mission have the moral authority to make that decision on behalf of people who don't exist yet. And there is no clean answer. There is no consensus. The debate is ongoing, and it matters because any serious proposal for a crewed interstellar mission will eventually have to confront it. But here is where the story pivots, where the weight of all these challenges, the radiation, the isolation, the generational complexity, the ethical questions, the sheer duration, meet something unexpected. People adapt. Profoundly, creatively, stubbornly, beautifully, people adapt. The history of humanity is, at its core, a history of adaptation to environments that should have been impossible to survive in. Our ancestors crossed open ocean in outrigger canoes with nothing but stars and wave patterns to navigate by. They lived through ice ages that reduced the global human population to perhaps a few thousand individuals. They built civilizations in deserts, in Arctic tundra, in dense rainforest, in high-altitude mountains where the air carries barely enough oxygen to sustain consciousness. Every time the environment said, "This is the limit," some subset of humanity looked at the limit and decided it was a starting point. The psychology of adaptation in isolated, high-stress environments has produced some of the most interesting research in modern behavioral science. Studies of Antarctic winter-over cruise, small groups of people who spend months in near-total isolation in one of the most extreme environments on Earth, have consistently found that after an initial adjustment period, most people develop sophisticated coping mechanisms, build meaningful social bonds, and report deep personal growth from the experience. The most successful groups are those with clear shared purpose, equitable distribution of responsibilities, and strong mechanisms for conflict resolution. There's a term researchers use for the psychological transformation that can occur during prolonged isolation with a clear, transcendent purpose, post-traumatic growth. Not the absence of difficulty, but the presence of meaning that transforms difficulty into something generative. Astronauts describe it. Polar explorers describe it. Long-distance solo sailors describe it. And while a generation ship is an order of magnitude more extreme than any of these analogies, the underlying human capacity for meaning-making doesn't have an obvious ceiling. Now, let's talk about what you're actually seeing out the window. Because by year 10 of your journey, a full decade after departure in 2026, the universe around you has begun to reveal something it hides from observers inside the solar system. Gamma rays, X-rays, the full unfiltered electromagnetic spectrum. From Earth, our atmosphere blocks most of the electromagnetic spectrum, Visible light gets through, some radio waves, some infrared, but the high-energy end of the spectrum, X-rays, gamma rays, ultraviolet radiation, is largely absorbed by the upper atmosphere before it reaches the ground. This is, of course, enormously beneficial for life. It's also an observational limitation. Space-based telescopes like the Chandra X-ray Observatory, the Fermi Gamma Ray Space Telescope, and the XMM Newton Observatory have given us extraordinary views of the high-energy universe. But they're still operating from inside, or very close to, the heliosphere, with all its associated magnetic fields and particle environments. Your vessel, now deep in the interstellar medium, has access to a radiation environment that is more uniform, more predictable, and in some ways more scientifically valuable than anything available from Earth orbit. The cosmic background radiation, the faint, uniform microwave glow left over from the early universe, released approximately 380,000 years after the Big Bang, is detectable with extraordinary precision from interstellar space, with none of the foreground contamination from the sun and the solar wind that ground-based and near-Earth observations have to painstakingly filter out. And then there are the cosmic rays. Those high-energy particles that are a threat to the crew are simultaneously one of the most scientifically interesting things in the local universe. The highest energy cosmic rays, called ultra-high energy cosmic rays, carry energies that dwarf anything produced by our most powerful particle accelerators. The most energetic cosmic ray ever detected, recorded in 1991 and nicknamed the Oh My God particle, carried an energy equivalent to a baseball pitched at about 90 kilometers per hour, compressed into a single subatomic particle. Where these particles come from, what astrophysical process produces them, is still genuinely an open question. Being outside the heliosphere, with detectors sensitive to their arrival direction and energy spectrum, could provide data that no Earth-based or near-Earth observatory can match. By the time your vessel reaches the quarter-light-year mark, 25 years into the journey, roughly the year 2051, something else has shifted, something subtle but measurable in the star positions around you. Parallax, the apparent shift in star positions caused by your change in location relative to Earth. From Earth, parallax measurements are made by observing how nearby stars appear to shift against the background of more distant stars as Earth moves from one side of its orbit to the other, a baseline of about 300 million kilometers. This is how we measure stellar distances. The parallax method is the foundation of the entire cosmic distance ladder. From a quarter light-year away, your baseline is over 15 trillion kilometers, about 15,000 times larger than Earth's orbital diameter. The parallax shifts for nearby stars are now large enough to be directly visible, not just measurable by instrument. Stars that appeared close together from Earth now show clear separation. The three-dimensional structure of your immediate stellar neighborhood, the true spatial relationships between nearby stars, becomes apparent in a way that no Earth-based observation can replicate. You can see where you are in space, not inferred from calculations, directly visually evident in the changed sky around you. And the star you're traveling toward, if your mission has a destination, is no longer a point in the distance. Over decades, at 1% of light speed, its parallax shift accumulates. Its spectrum, studied continuously with the ship's instruments, begins to reveal its character, its temperature, its activity cycle, its magnetic field, the chemical composition of its atmosphere, the presence or absence of infrared excess that might indicate a debris disk, the signature of planets. You are doing science that cannot be done from Earth, science that couldn't be done until you left, and the data you're transmitting back, across a growing gulf of light travel time, arriving at Earth a quarter year after you sent it is changing what humanity knows about the universe in real time. There is a particular moment in the journey. I imagine it happening at night, during whatever passes for night on a vessel with an artificial day cycle, when one of the crew floats to a viewport and looks out, and the thought arrives not as a concept but as a direct bodily experience. Every human being who has ever lived was born, grew old, loved, suffered, created, and died within a sphere of space roughly a few hundred kilometers thick, wrapped around a single planet. Every war, every great work of art, every scientific revolution, every act of cruelty, and every act of extraordinary kindness, every child who ever looked up at the stars and wondered, all of it compressed into a thin film of atmosphere and rock and ocean on one world, orbiting one star, in one arm of one galaxy, among hundreds of billions, and you are outside of it, moving away from it, still connected by a thread of radio signal that takes months to travel in either direction. Still human, still made of the same atoms, still carrying the same evolutionary history encoded in every cell of your body, but outside, further from Earth than any human being has ever been, and getting further with every second. Carl Sagan called Earth the pale blue dot. He described it as a mote of dust suspended in a sunbeam, a tiny, fragile, irreplaceable speck in the vast cosmic dark. He wrote those words looking at a photograph taken by Voyager 1 from about 6 billion kilometers away, less than 1/10 of 1 light year from the quarter light year mark. Earth is not even a dot anymore. It's lost in the glare of the sun, a point of light indistinguishable from the star that holds it. And yet, and this is the thing that Sagan understood so deeply, the thing that science at its best always circles back to, the fact that we can conceive of this journey, that we can do the mathematics, build the telescopes, write the mission plans, ask the questions, feel the awe, argue about the ethics, and dream about the stars. That is not a small thing. That is, in the context of everything we know about the universe, a staggering and improbable thing. The cosmos made something that can look at itself and wonder, and that something, right now, is you. If you are enjoying this journey, make sure to give this video a like and subscribe. The next time the universe hands you a question this big, you'll already be here for the answer. Now let's go to 50 years after departure. The year is 2076. Half a century since the vessel left Earth orbit in 2026, and somewhere in the interstellar dark, moving at 1% of the speed of light, the ship crosses a threshold that no instrument announces and no alarm marks, but that every crew member old enough to understand. It feels in a way that goes beyond numbers, the halfway point, 0.5 light years from Earth. 0.5 light years from the destination. For the first time in the mission's history, you are closer to where you're going than to where you came from. It sounds simple. It is not simple at all, because the people celebrating this moment, if celebrating is the right word, and it might not be, are not the people who left. The founders of the mission, the ones who strapped in and felt the acceleration and watched Earth shrink in the viewport, are gone. Some died of old age, some of illness, some perhaps of things that happen in small communities under enormous pressure over long periods of time, the kinds of things that history books record carefully and mission planners work desperately to prevent. The people at the halfway point are their grandchildren, born on the ship, raised on the ship. The only home they have ever known is a vessel with a fixed volume, a recycled atmosphere, artificial lighting that mimics a day cycle their bodies were designed for but have never experienced naturally, and a sky that, outside the viewports, has barely changed in their entire lifetimes. What do these people know about Earth? This is one of the most philosophically rich questions in the entire architecture of a generation ship mission, and it's one that actual researchers, sociologists, anthropologists, space mission architects, have begun to take seriously in recent years. The work of Dr. Cameron Smith at Portland State University, for instance, has focused on the population genetics and cultural transmission challenges of generation ships. His models suggest that a minimum crew of around 10,000 to 40,000 individuals would be needed to maintain sufficient genetic diversity across multiple generations to avoid the compounding health problems caused by inbreeding in small, closed populations. Most popular generation ship proposals feature crews in the hundreds or low thousands, numbers that, genetically speaking, are dangerously small over the timescales involved. But beyond genetics, there's the question of cultural transmission. How do you pass on not just knowledge, facts, skills, technical competencies, but purpose? How do you ensure that the third generation, the fourth, the fifth, still understands why this mission exists, still feels the weight and meaning of a choice that was made before they were born, by people they know only through records and stories? Every human civilization has grappled with versions of this problem. Religious traditions, legal systems, cultural practices, all of them are, at some level, mechanisms for transmitting meaning across generations. And all of them, over long enough timescales, drift. Languages evolve, interpretations shift. The meaning encoded in a founding document 300 years ago is not the meaning that most people reading it today would reconstruct from scratch. On a generation ship, this drift could be mission critical. If the fifth generation has, through 200 years of cultural evolution in isolation, developed a significantly different understanding of the mission's purpose, or worse, has organized itself around values that are fundamentally incompatible with arriving at the destination and doing something useful, the entire multi-century investment of the civilization that launched them is lost. Mission architects call this the purpose drift problem, and there is no solved engineering answer to it. The best proposals involve redundant, physically distributed archives of mission documentation that cannot be altered by any individual or governing body on the ship, combined with cultural institutions, what some researchers call mission religion, not in a theological sense, but in the sense of regularly practiced, communally reinforced ritual that keeps the mission's core meaning alive and felt, not just known. Now let's talk about the ship itself, because 50 years is a very long time for mechanical and electronic systems to operate without failure in an environment that offers no possibility of resupply, no possibility of calling a repair team, and no possibility of abandoning the mission and coming home. The engineering philosophy required for a generation ship is fundamentally different from anything humanity has built before. Every system that is critical for survival must be redundant, not just doubled but tripled or quadrupled. Every component must either be replaceable using materials available on the ship or must have a designed lifespan far exceeding the mission duration. The vessel must be capable of manufacturing its own spare parts, growing its own food, recycling essentially 100% of its water and atmospheric gases, and generating its own energy without any external input other than whatever the propulsion system provides. Food production is one of the most complex challenges. The most efficient closed-loop agricultural systems currently being studied, largely driven by interest in long-duration Mars missions and space station food independence, combine hydroponic and aeroponic plant cultivation with insect protein production and potentially cultured meat technologies. The caloric density and resource efficiency of insect farming, in particular, makes it attractive for space applications. Crickets, for instance, require roughly 12 times less feed than cattle to produce the same amount of protein, produce virtually no methane, and can be farmed in very small volumes. A diet built substantially around insect protein combined with hydroponic vegetables, legumes, and algae cultivation, could theoretically sustain a crew indefinitely in a closed system. Theoretically, because every theoretically in a generation ship design is hiding an engineering challenge that could take decades to solve. Algae cultivation at scale produces oxygen and protein efficiently, but requires careful management of light exposure, CO2 levels, and nutrient cycling. Hydroponic systems are vulnerable to pathogen outbreaks that, in a closed environment with no access to fresh genetic stock, could devastate crop yields in ways that would be catastrophic on the timescales involved. The redundancy required isn't just mechanical, it's biological. Energy generation is the other pillar everything else rests on. A vessel at 1% of the speed of light in the interstellar medium is too far from the sun for solar power to be meaningful. The intensity of sunlight falls off with the square of the distance, and at half a light year, it is completely negligible. Nuclear fission and nuclear fusion are the serious candidates. Fission reactors, the technology we already use in nuclear submarines and power plants, are well understood, compact enough for spacecraft applications, and capable of providing consistent power output over long periods. The challenge is fuel longevity. A century-long mission requires either an enormous initial fuel load or the ability to breed additional fissile material from fertile isotopes on board. Nuclear fusion, the process that powers stars, fusing light nuclei together to release energy, is the more attractive long-term option because the fuel, primarily hydrogen and its isotopes, is vastly more energy-dense than any fission fuel. A fusion-powered generation ship could, in principle, carry enough fuel for the entire journey in a volume that fission could never match for the same energy output. The challenge is that sustained, controlled nuclear fusion for power generation has been 20 years away for approximately 60 years. The National Ignition Facility achieved fusion ignition, more energy out than laser energy in December 2022, a genuine milestone. ITER, the International Fusion Reactor being built in southern France, is scheduled to begin plasma operations in the early 2030s and achieve full fusion power by the early 2040s. Progress is real and accelerating, but a fusion reactor reliable enough to run for a century without maintenance in the interstellar medium with no external support, that is an engineering goal several generations beyond what we currently have. By year 50, the crew, now the second and early third generation, has also developed something that the mission planners might not have fully anticipated: a culture. Not the culture they were given. Their own language drifts. Over 50 years in isolation, with a founding crew drawn from multiple national and linguistic backgrounds, the spoken language of a generation ship would evolve, borrowing, blending, shedding words that refer to things that no longer exist in this environment, inventing words for things that have no earthly equivalent. The color of artificial light after the third major replacement of the lighting system, the specific sound the atmospheric recyclers make during a maintenance cycle, the feeling of being in a section of the ship that has been sealed off for years for reasons that are now debated rather than remembered. Art would emerge. Music calibrated to the acoustic properties of the ship's interior, a resonance profile unlike any concert hall, any outdoor space, any room on Earth. Visual art responding to a sky that has no horizon, no weather, no seasons, no dawn, stories. The kind of narrative structures that every human community generates to explain who it is and where it came from, and what it owes to those who came before and those who will come after. And religion, possibly, probably, versions of the meaning-making structures that human beings have generated in every culture, in every environment, throughout our entire recorded history. Whether those structures would resemble any earthly tradition is genuinely unknowable, but the need they serve, the need for framework, for purpose, for a shared story that places individual life within a larger context. That need doesn't switch off in space now. Year 60, 2086. Something happens that the mission architects hoped for but could not guarantee. Something that changes the emotional texture of the entire remaining journey. The ship's long-range instruments, far more sensitive than anything the founding generation launched with, because the second and third generations have had decades to refine and improve the onboard detection systems, pick up a signal, not a communication signal, not a sign of intelligence. Something more scientifically fundamental, an exoplanet atmosphere spectroscopic signature from the target system. Let me unpack what that means. When a planet passes in front of its host star as seen from a particular vantage point, starlight filters through the planet's atmosphere. Different molecules in that atmosphere absorb different wavelengths of light. By analyzing the spectrum of the filtered starlight, looking for the characteristic absorption lines of specific molecules, you can determine the chemical composition of the atmosphere. From Earth or from near-Earth space telescopes like JWST, this technique, called transmission spectroscopy, is already being used to study exoplanet atmospheres across dozens or hundreds of light years. The James Webb Space Telescope has already detected carbon dioxide, methane, water vapor, and sulfur dioxide in the atmospheres of planets orbiting other stars from 60% of a light year away. Moving directly toward the target system, the signal clarity is extraordinary by comparison, and what the ship's instruments find in that filtered starlight is this: oxygen, nitrogen, water vapor, carbon dioxide at levels consistent with a biological carbon cycle. And this is the part that stops everything: a faint but measurable signature of methane present at concentrations that, given the simultaneous presence of oxygen, cannot be maintained by geological processes alone, because oxygen and methane react with each other. In the presence of both in equilibrium, there must be an ongoing source replenishing one or both of them continuously. On Earth, that source is life. The people who detect this signal are the grandchildren of the people who left Earth in 2026. They were born into a mission whose purpose they inherited, but whose full weight they had absorbed slowly, intellectually, over years of education and cultural transmission. They understood it. They were committed to it. But now they feel it. Now it is not a mission inherited from ancestors they know only through recordings and journals. Now it is the most important thing any human being has ever done. They are 60% of the way to a world that the data strongly suggests is alive, and they are the ones who are going to get there, not their grandparents, not future descendants. Them, the people alive on this ship right now, in the year 2086, moving through the interstellar dark at 3 million kilometers per hour toward a pale point of light that is getting almost imperceptibly brighter. What does that moment do to a community? What does it do to the social fabric of a vessel that has been managing the slow, grinding psychological weight of an intergenerational mission for 60 years? What does it do to the way people sleep, eat, argue, love, grieve, create? I think it does what great discoveries have always done throughout human history. It makes the suffering retroactively meaningful. It transforms the narrative from "we are people who gave up everything for a mission we might never see completed" into "we are the people who are going to be the first human beings to stand in the presence of life that evolved under a different star." And nothing, not the radiation, not the isolation, not the ethical complexity, not the grief of generational separation from everything humanity ever built on Earth, nothing takes that away. There is a problem that every interstellar mission architect eventually arrives at, and it is one that receives a fraction of the attention given to propulsion, shielding, or food production. It is, in some ways, more fundamental than any of those. More fundamental because without solving it, arriving at the destination is not a triumph. It is a disaster in slow motion. The problem is this: how do you stop? It sounds almost embarrassingly simple when you say it out loud, but the physics underneath it are brutal and unforgiving. Accelerating a vessel to 1% of the speed of light requires an enormous expenditure of energy. Decelerating that same vessel, bringing it from 3 million kilometers per hour back to something approaching orbital insertion velocity around a new star system, requires an equal and opposite expenditure of energy. There is no brake pedal in interstellar space. There is no atmosphere to aerobrake in, not at those velocities and not at those distances from any usable planetary body. Every unit of deceleration has to be produced by the propulsion system running in reverse, which means the ship needs, at minimum, enough fuel remaining at the halfway point to decelerate the entire remaining mass, ship plus crew plus cargo plus remaining fuel, for the second half of the journey. This is known in orbital mechanics as the tyranny of the rocket equation, named after the Tsiolkovsky rocket equation derived by Russian mathematician Konstantin Tsiolkovsky in 1897. The equation describes a relationship that is simultaneously elegant and merciless. The faster you want to go, and the more mass you're carrying, the exponentially more fuel you need. And fuel has mass. So more fuel requires more fuel to carry it, which requires more fuel. The equation spirals against you with a mathematical ruthlessness that has haunted propulsion engineers for as long as the discipline has existed. For a journey to 1 light year and back, or even one way with a controlled arrival, the fuel mass fraction required under conventional propulsion is essentially prohibitive. This is one of the primary reasons that proposals for interstellar travel that take the rocket equation seriously tend to look radically different from conventional spacecraft. Solar sails and laser propulsion avoid the problem on the acceleration side by not carrying propellant at all. The push comes from photons, not from onboard fuel. But deceleration is still required. Proposals include using the magnetic field of the destination star system to create drag, a kind of electromagnetic braking, or deploying a massive forward-facing sail that uses the pressure of the destination star's light to slow down, the same way a laser drove the ship up to speed in the first place. Neither of these solutions is fully developed. Both are physically plausible, and in the context of our journey, a crewed vessel at 1% of light speed, the deceleration phase begins at the halfway point and consumes exactly as much time and energy as the acceleration phase. 25 years to slow down. 25 years during which the engines are running continuously in the forward direction, pushing against the ship's momentum, trading kinetic energy for the ability to actually stop when you get there. The year is 2101. 75 years into the journey, the third and fourth generations of crew are alive. The founding generation are names in a historical archive. Some of them are remembered as individuals: the mission commander, the chief engineer, a botanist who spent 40 years developing the crop strains that feed everyone on board, a child psychologist who designed the educational framework that has now been running for 3 generations. Others have blurred into the collective memory of the founders, people who made a choice that determined the shape of every life that followed. The deceleration burn has been running for 25 years. The ship is slowing. The star ahead, which has been a point of light for the entire journey, has now resolved into something different. Not a disk yet, not to the naked eye, but to the instruments. It is a star with a personality, a measurable luminosity, a precise spectral type, a detected magnetic activity cycle, a confirmed planetary system whose architecture has been mapped with increasing resolution over the last several decades of approach. And somewhere in that planetary system, confirmed now by multiple independent measurement methods, confirmed to the satisfaction of every scientist on board and every scientist on Earth who has received the data transmissions, confirmed beyond what any reasonable threshold of doubt could ask for. There is a world with an oxygen-nitrogen atmosphere, liquid water on its surface, and biosignatures consistent with biological activity. A living world. Under a different sun, let me describe what the approach actually looks like. Because this is the part of the story that deserves to be felt, not just understood. At 75 years out from Earth, 0.75 light-years, the destination star is bright enough that it has become the dominant light source visible from the ship. Not brighter than Earth's sun was at departure, but now, after 50 years of the sun fading behind you, it is the star that casts shadows inside the viewport bays, the star you're decelerating toward, the star that for the third and fourth generation crew is not a destination but a home, not the home of their ancestors. Their home, the star, is a K-type star, what astronomers call an orange dwarf, slightly smaller, slightly cooler, slightly dimmer than our own G-type sun. Orange dwarfs are considered by many astrobiologists to be among the most promising hosts for life-bearing planets, for a fascinating set of reasons. They burn their hydrogen more slowly than sun-like stars, giving them lifespans of 15 to 30 billion years, 2 to 3 times longer than our sun's expected 10 billion year life. They are less prone to the violent stellar flares that can strip away a planet's atmosphere, particularly in a planet's early history. And the habitable zone, the range of orbital distances where liquid water can exist on a planet's surface, is close enough to the star that a tidally locked planet, while possible, is not inevitable for all worlds in the zone. The world your instruments have been studying. Let's call it what the crew would almost certainly call it, eventually, after decades of debate and cultural negotiation, the second world, or simply the other world, orbits at a distance that keeps its surface temperatures within the range where liquid water can exist across most of its surface. Its day is longer than Earth's. Its gravity, based on its measured mass and radius, is slightly lower, perhaps 85% of Earth's surface gravity, low enough to be immediately noticeable, not so low as to pose serious long-term health risks beyond what decades of ship life have already introduced. Its atmosphere, as measured by transmission spectroscopy over 70 years of increasingly precise observations, is thicker than Earth's. The surface pressure is probably higher. The oxygen concentration is lower, perhaps 15% compared to Earth's 21%. Breathable but thinly, the kind of air that would leave an unacclimatized person slightly breathless on exertion, the kind of air that after a generation of adaptation would feel perfectly normal. But before we talk about landing, before we talk about the moment any human foot touches the surface of another living world, we need to talk about the signal, because 60 years ago, when the biosignature detection changed everything on the ship, the crew transmitted the data back to Earth. A compressed, carefully encoded data package containing every spectroscopic measurement, every statistical analysis, every cautious but unmistakable conclusion. And that transmission, traveling at the speed of light, took 0.6 years to reach Earth, roughly 7 months. Earth received the signal around the year 2087. Try to imagine what that moment looked like from the other end. Not from the ship, from Earth. From a civilization that launched a crew into the dark in 2026, has been receiving irregular data transmissions for 60 years, and has been watching the slow accumulation of exoplanet data with a combination of scientific excitement and genuine existential uncertainty that any honest person would feel. And then one day, a specific day, a day that would be remembered, the data arrives, and the analysis is clear, and the conclusion, stated carefully and precisely by scientists who have spent their careers being rigorous and skeptical, is that there is biological activity on a world orbiting another star. The philosophical, cultural, religious, and scientific impact of that moment, even from 60 light years away in a metaphorical sense, even from a crew that is nowhere near landing and is still decades away from arrival, would be the most significant event in human intellectual history. Bar none. Nothing we have ever discovered, nothing we have ever built, nothing we have ever understood about the universe would carry the same weight as confirmation that biology is not a one-time event. That life, in whatever form, is something the universe does more than once. The Fermi paradox would become simultaneously more and less mysterious. More, because if life can arise independently in two star systems separated by less than 1 light-year, neighboring systems, cosmically speaking, then it should be everywhere. And if it's everywhere, where is everyone? Why is the universe so quiet? Less mysterious because at least we would know, for certain, not as a statistical argument or a philosophical inference, but as a confirmed observational fact, that we are not alone, that the universe, in its indifference, managed to produce biology twice. At minimum, the signal back from Earth, confirming receipt, confirming the scientific community's response, telling the crew what has happened on the civilization they left behind, takes 0.6 years to arrive, and by the time it does, the crew has already been living with the knowledge for 7 months. The response from Earth is, by all accounts in this imagining, overwhelming, a torrent of transmissions, scientific responses, philosophical responses, religious responses, political responses, personal messages from the families of crew members who are now on their 2nd or 3rd generation removed from direct family connection with anyone on Earth. The crew reads these messages over weeks, months, and what they feel is complex, pride, validation, a deep, complicated form of grief for a home that is now 63 years of light travel time away, and something else that's harder to name, a recognition that they have become, whether they chose it or not, the most important people in the history of their species, not because of talent or ambition, because of time and trajectory and the compounding of choices made before they were born now. Year 90, 2116. The ship is close enough to the destination star system that its planets are no longer just spectroscopic signals. The outer gas giant, a large world orbiting far from the star, detected years ago by its gravitational wobble, is now visible as a disk in the ship's optical instruments. Its moons are visible as separate points of light. The system is revealing its architecture. One large outer gas giant, 2 smaller rocky inner worlds in the inner system, and the living world sitting in the middle of the habitable zone with a single large moon, slightly larger relative to its planet than our moon is to Earth, that stabilizes its axial tilt in the same way our moon stabilizes ours. That stability matters. A stable axial tilt means stable seasons. Stable seasons mean stable, predictable climate patterns over geological timescales. Stable climate means evolutionary time, the long, uninterrupted stretches of consistent environmental pressure that allow complexity to emerge from simplicity, that allow single cells to become multicellular organisms, that allow life to experiment and fail and try again across billions of years of deep time. The world ahead has had that stability. For how long is uncertain. The age of the star system, estimated from stellar evolution models, is approximately 6.8 billion years, older than our solar system by about 1.8 billion years. Whatever is alive there has had more time than we have had, more time to evolve, more time to develop, more time to become whatever it is that 70 years of spectroscopic observation has only seen the atmospheric signature of, and has not, despite extraordinary efforts, detected any radio emission, any laser signal, any artifact of technology from, Whatever lives there, it appears not to be technological, or if it is, it's not broadcasting in any frequency or modality the ship's instruments can detect. The Fermi paradox whispers quietly in the background of every conversation on board. Year 95, 2121. The living world is now visible to the naked eye as something more than a star. On the best optical nights, during the ship's dark cycle, when the viewport shutters open and the interior lights are dimmed, crew members gather to look at it. A point of light, slightly blue-green in tint, that moves perceptibly against the background stars from one observation to the next. Perceptibly, to the naked eye, it is not a concept anymore, not a dataset, not a biosignature. It is a place, a world, sitting there under its orange sun, doing whatever it is doing in complete indifference to the fact that 4 generations of human beings have spent a century crossing the dark to reach it. And the 5th generation, the children of the 4th, born in the last decade of the journey, who will be teenagers and young adults when the ship finally achieves orbital insertion. Look at that blue-green point of light, the way the very first humans must have looked at the horizon. Not with the abstract wonder of someone who understands the scale intellectually, with the direct embodied, hungry wonder of someone who knows, in their bones, that something extraordinary is waiting just beyond what they can currently see. They are the ones who will go down, if going down is the decision that's made. And that decision, whether to orbit, study, send probes, maintain distance, or actually land, is one of the most consequential choices in all of human history. And it is a choice that the people on this ship will have to make largely on their own, because any request for guidance sent to Earth takes 1 light year, 1 year to arrive, and the reply takes another year. In a situation that might require a decision in days or weeks, Earth is functionally unreachable. They are on their own. They have always been on their own. And now finally they are also almost there. Year 98, 2124. The main deceleration burn has been running for 48 years. The vessel's velocity has dropped from 3 million kilometers per hour to something approaching orbital insertion range. A few tens of thousands of kilometers per hour relative to the destination star. The engines are running at their lowest sustained output now, trimming velocity with a precision that the founding generation could only have dreamed of achieving with the instruments they launched with. The 3rd and 4th generation engineers, people who have spent their entire lives inside this ship, who know its systems the way a farmer knows their land, the way a musician knows their instrument, have spent decades refining the control algorithms, replacing worn components with parts fabricated on board, solving problems that the original mission designers never anticipated because no one had ever done this before. No one has ever done this before. That thought sits differently at year 98 than it did at year 1. At year 1 it was thrilling. At year 98 it is simply the texture of daily life. The weight of being first is something you carry for so long that it stops feeling like a weight and becomes simply part of your skeleton. The living world is now close enough that the ship's highest resolution optical system can resolve surface features, not details, not terrain, but the broad brushstrokes of a planetary surface, the distinction between what appears to be open ocean and what appears to be landmass, the presence of what look like weather systems, cloud formations that evolve over hours of observation, that move across the surface in patterns that speak of an atmosphere with dynamics, with energy cycling, with the same basic thermodynamic machinery that drives Earth's weather. A planet with weather, a planet with oceans, a planet with an atmosphere full of oxygen that something biological is producing and maintaining. The 5th generation, the youngest crew members, some of them barely adults, spend their off hours at the viewport bays in groups, watching that growing disk in shifts, not studying it scientifically, just watching. The way you watch something that you understand in your deepest interior is going to change your life. But before we go any further into the approach, we need to stop and have the conversation that the mission planners started having in the 2020s, that every generation of crew has revisited, and that is now, at year 98, with the surface of an alien world resolving in the instruments, no longer theoretical. The contamination question, it sounds technical. It is not just technical. It is one of the most genuinely difficult ethical problems in the entire history of science, and it cuts in two directions simultaneously, which is what makes it hard. Direct one, forward contamination. The risk that a crewed vessel or any probe, any lander, any object of human origin carries microbial life from Earth to an alien biosphere. Earth organisms are extraordinarily robust. Bacterial spores can survive vacuum, radiation, and temperature extremes that would kill any complex organism. If even a single viable Earth microorganism reaches the surface of a world with liquid water and a hospitable temperature range, the consequences are genuinely unknowable. It might die immediately. It might survive but fail to establish. It might establish, reproduce, and interact with the native biosphere in ways that range from negligible to catastrophic. In the worst case, an Earth microorganism introduced to an alien biosphere that has no evolutionary history with it could spread in ways that fundamentally alter or destroy the very thing the mission spent a century crossing the galaxy to study. The scientific tragedy of that outcome is obvious. You traveled 1 light year to find alien life. You contaminated it. Now you can never be sure whether what you're observing is alien biology or Earth biology, or some impossible entanglement of both. The thing you came to understand has been irrevocably changed by the act of your arrival. Direct 2. Backward contamination. The reverse problem. Alien biology, microorganisms, biochemical compounds, anything biologically active from the native world, reaching the crew and the ship. Human immune systems are the product of billions of years of coevolution with Earth's biosphere. They are extraordinarily sophisticated at recognizing and responding to threats that share Earth's biochemical framework. An alien organism, if it has biology at all, if its chemistry is built on anything approaching the carbon-water framework we're familiar with, might be completely invisible to human immune defenses. Or it might interact with human biology in ways that produce effects no medicine derived from Earth experience could predict or treat. The Outer Space Treaty of 1967 already contains language about planetary protection, about the obligation of spacefaring nations to avoid harmful contamination of celestial bodies and to avoid adverse changes to Earth's environment through the introduction of extraterrestrial matter. The COSPAR, the Committee on Space Research, has developed planetary protection policies that currently govern the design and sterilization of all missions to potentially habitable bodies in our solar system. Mars, Europa, Enceladus, all of them require strict contamination protocols. For a crewed mission to a confirmed living world 1 light year away, those protocols would need to be orders of magnitude more rigorous. And here is the brutal reality: they cannot be perfect, not with a crewed ship, because humans are biological. We shed skin cells, we breathe. Our gut microbiomes are diverse ecosystems of hundreds of species. Complete biological isolation between a crew and an alien environment is not achievable with any technology we currently possess or can plausibly develop. This is why serious proposals for first contact with alien biology almost universally begin with robotic precursor missions, sterile probes, orbiters and remote sensing, decades of remote observation before any decision about surface contact is made, and on a generation ship that has traveled for a century to get here, the patience required to then spend additional years or decades in remote observation. So close, so tantalizingly close, with a living world visible through the viewport, is a psychological and cultural challenge of enormous proportions. The debate on board in year 98 is real, sustained, and often heated in the way that all genuine moral debates are heated, not because people disagree about the facts, but because they weight the values differently. Some crew members argue for immediate robotic probe deployment, sterile, purpose-built probes that can enter the atmosphere, image the surface, collect and analyze samples remotely, and transmit data back to the ship, all without any biological material from Earth making contact with the native environment. This faction emphasizes the scientific integrity of the mission, the ethical obligation to the alien biosphere, and the irreversibility of contamination. Once you contaminate something, you cannot uncontaminate it. You cannot run the experiment again. Others argue differently. They have been born and grown and lived and watched people they love age and die in this ship. They are not abstractions. They are not mission parameters. They are human beings with exactly one life, and that life has been shaped entirely by this journey and the idea of arriving at a living world and spending additional years or decades in cautious, remote observation when the surface is right there, when the ocean reflects the orange starlight right there in the instruments, when the atmospheric wind patterns have been studied so thoroughly that they know the seasonal cycle of a world they've never touched. That idea produces in them something that is not recklessness. It is hunger, the same hunger that drove the founding generation to get on the ship in the first place. There is no clean resolution. There is no answer that satisfies everyone. There is only the process, the sustained, careful, democratic process of a community making the most consequent decision it has ever faced, together with full awareness that whatever they choose, the people on Earth will not know the outcome for at least 1 year after it happens. Year 99, 2125, the ship achieves orbit, not around the living world directly, not yet. First, the vessel enters a wide orbit around the destination star, using the star's gravity to reduce velocity further, while the crew and the scientific team complete their initial high-resolution survey of the planetary system. The outer gas giant passes at a distance, enormous, banded in subtle colors, with a ring system thinner than Saturn's but unmistakably present. Its moons are varied and strange. One of them, a medium-sized icy body in the outer part of the gas giant's moon system, has a surface that the spectrometers say contains complex organic compounds, not life, not biosignatures, but chemistry. The building blocks of something. The chemistry of this system is not identical to Earth's, but it rhymes. The rocky inner world, the smaller of the two inner planets, closer to the star, is airless and heavily cratered, ancient, a record of the system's early violent history written in impact scars across its face. The second inner rocky world, between the airless one and the living world, has a thick carbon dioxide atmosphere, a pressure at the surface somewhere between 3 and 5 times Earth's at sea level, and surface temperatures hot enough to melt certain metals, an extreme greenhouse, like a more intense version of Venus. The living world, sitting in the orbital sweet spot between these two, seems to have navigated the atmospheric evolution problem that Venus failed, retaining water, maintaining a carbon cycle, keeping temperatures within the range that liquid water requires. How? That is one of the great questions of planetary science. Why Earth kept its water and Venus didn't, given that they formed in similar regions of the same solar system. Understanding how this other living world solved the same problem from a completely independent starting point could be one of the most scientifically valuable things the mission returns, not just for pure knowledge, for understanding the future of Earth itself, whose long-term atmospheric trajectory under an increasingly luminous sun eventually leads in the same direction as Venus. 3 months into the stellar orbital survey, the first probe is ready, sterile, built from materials that were kept in sealed cleanroom conditions since manufacture, handled only by robotic systems, never exposed to the biological environment of the ship. Small, roughly the size of a briefcase, carrying a suite of instruments, cameras across multiple wavelengths, an atmospheric sampler and analyzer, a ground-penetrating radar, a seismometer for measuring surface vibrations, and a direct sample analysis system that can perform basic biochemistry on collected material without returning that material to the ship. The probe is released. It fires its small engine. It begins the slow spiral inward through the system toward the living world. Everyone on the ship watches the telemetry. The entry into the living world's atmosphere takes 47 minutes. The probe's heat shield glows. The atmospheric sampler activates, pulling in and analyzing the surrounding gas in real time. The oxygen reading comes back first, 15.3%, then nitrogen 78.1%, then the trace gases, carbon dioxide, argon, water vapor, and then methane 0.0018%. Tiny, but there, exactly where the spectroscopic observations from space predicted it would be, the parachute deploys. The probe descends through clouds, water clouds, the same white and grey layered structures that every human being who has ever looked up at Earth's sky has seen, and emerges below them into clear air. And the cameras come on. What comes back is, for a few seconds, incomprehensible to the people watching it. Not because it's alien in the way science fiction has always imagined alien. Not because it's strange and crystalline and geometrically wrong. It's incomprehensible for the opposite reason. It looks like a place, not a planet. A place. Something the human visual cortex, shaped by millions of years of evolution on Earth, calibrated to read terrain and horizon and sky, immediately and involuntarily recognizes as a place. There is a horizon, there is a sky, slightly more orange-tinged than Earth's because of the star it's lit by, but a sky scattering light through an atmosphere in the same basic way Earth's atmosphere does. There is what appears to be flat ground, a coastal area or a dry lakebed or a plain. It's hard to tell, covered in something low, something dense, something that shifts color slightly across the frame in patterns too consistent to be geology, something that is, almost certainly, alive. Not animals, nothing moving, nothing with obvious structure or form, but a surface covering of what the spectrometers immediately begin analyzing and finding to contain chlorophyll-like pigments, molecules that absorb light and use the energy to drive biochemical reactions. Photosynthesis, or something that performs the same function using the same basic principle, developed independently on a world that has never had any contact with Earth. The convergent evolution of photosynthesis, twice. In 2 separate solar systems, the scientist on duty when the data comes back is a 23-year-old woman, 5th generation, born on the ship, has never stood on a planetary surface of any kind, has never felt weather or wind, or the specific quality of light that comes through an atmosphere rather than a viewport. She has spent her entire education preparing for exactly this moment. She has been calm and professional through the entire probe descent, calling out telemetry readings in a clear voice, logging data precisely when the camera image appears on the main screen. That impossible, familiar, planet-looking place, covered in something alive. She is quiet for a long moment, and then she says, simply, to no one in particular and to everyone at the same time, "It's everywhere," meaning the life, meaning the living surface covering. The alien photosynthesizers are not confined to a patch or a region. They cover the ground as far as the camera can see, in every direction, the way grass covers a meadow or lichen covers a rock face. Not everywhere on the planet, but here in this coastal plain, in the orange-lit afternoon of a world that has been alive for longer than our sun has existed. Life is everywhere, The signal takes 1 light year to reach Earth, 1 full year of travel at the speed of light. The people who transmitted it will be waiting 14 months for a reply, accounting for the transmission time in both directions. In 14 months, Earth will know. The civilization that launched this mission nearly a century ago, that has been aging and changing and, let's be honest, struggling with all the ordinary and extraordinary difficulties of being human on a single fragile planet, will receive confirmation that the universe is not empty, and whatever humanity does with that knowledge, whatever philosophical, cultural, spiritual, and scientific transformation follows, begins with a 23-year-old woman who grew up in a ship between the stars, looking at a camera image of a world no human being has ever touched, saying 4 words that contain the entirety of what that moment means. It's everywhere. If you are still watching, don't forget to subscribe and give this video a thumbs up. Every video we take a real question about the cosmos and follow it all the way down. No shortcuts, no fluff, just wonder. The ship is still in orbit. The probe is still transmitting. The living world is still turning slowly beneath its orange sun, covered in something alive that has never heard of Earth, never looked up at a night sky and wondered about the stars, never asked whether it was alone. The mission continues. The crew continues. The 5th generation is making decisions that will shape the 6th and the 7th, and every generation that follows them in that system, around that star, on that world or in orbit above it. But there is a conversation that this moment, the moment of confirmed alien life, demands we have. A conversation that goes beyond mission logistics and crew psychology and propulsion physics. A conversation about what this discovery actually means, not in the abstract, philosophical dinner party sense, in the deep, structural, world-rearranging sense, the kind of meaning that changes the foundations of how a civilization understands itself, because here is the thing about truly transformative discoveries. They don't just add information to what we already know, they retroactively change the meaning of everything we knew before. They don't expand the picture, they replace the frame. Consider what we understood about life before this moment. We had one example, Earth, a single data point. And in science, a sample size of one is not a sample size at all. It's an anecdote, a starting point, a placeholder until more data arrives. With only one example of life in the universe, we couldn't determine what was essential about life and what was accidental. We couldn't distinguish between the features of Earth life that reflect deep, universal principles of how biology works, and the features that are simply the particular, contingent, arbitrary path that one lineage of chemistry took on one planet around one star 4.5 billion years ago. Is DNA the only way to encode biological information? We didn't know. Is carbon the only viable backbone for complex biochemistry? We had arguments. Carbon's bonding versatility makes it uniquely suited, but we couldn't rule out silicon-based chemistry in extreme environments. Is photosynthesis an inevitable solution to the problem of capturing energy from a star? We suspected it might be, given how many times it evolved independently on Earth, in plants, in algae, in cyanobacteria, in certain species of bacteria living in conditions where almost nothing else survives. But we couldn't confirm it without a second example. Now we have a second example. And the alien photosynthesizers on the living world are using a chlorophyll-like molecule, not identical to Earth's chlorophyll, not the same protein structure, not the same exact pigment, but performing the same fundamental function, capturing photons, using that energy to drive chemistry, producing something analogous to what Earth's photosynthesizers produce. The convergence is not perfect, it is not a copy, but it rhymes closely enough that the underlying principle, use starlight to power biology, appears to be something the universe tends toward, given the right conditions. That single observation, that photosynthesis emerged independently in two separate solar systems is, scientifically, one of the most important things humanity has ever learned, because it begins to answer the deepest question in all of biology: how much of life is universal and how much is accident? The answer appears to be, more is universal than we dared hope. And that answer has a consequence that cascades through every field of human knowledge simultaneously. In astrobiology, the field dedicated to understanding life in the universe, it confirms what many researchers have long suspected but couldn't prove, that life, given liquid water, the right chemistry, and sufficient time, is not a miracle. It is not a vanishingly improbable accident that happened once and will never happen again. It is something the universe does, a process, a tendency, an emergent property of chemistry operating under certain conditions at sufficient complexity and duration. In cosmology, it reframes the question of the universe's structure. The universe is approximately 13.8 billion years old. Our solar system is 4.5 billion years old. That means there are star systems out there that have been around for 9 billion years longer than we have. If life emerges given sufficient time and the right conditions, and conditions similar to Earth's exist in a significant fraction of star systems, and the evidence increasingly suggests they do, given what the Kepler Space Telescope and TESS and JWST have revealed about the prevalence of Earth-sized planets in habitable zones, then the universe has been producing life for billions of years before our sun was born. Which means, and this is the thought that tends to make people quietly sit down, if life is common, and some of it has had 9 billion years more than we have, where is it? What has had 9 billion additional years to evolve, to develop technology, to expand, to communicate, to build something that lasts? The Fermi paradox in the wake of confirmed alien life does not get softer, it gets louder, because now we know that life exists elsewhere. We just don't know why it's quiet. There are several serious non-depissive answers to the Fermi paradox that researchers have proposed. Not we're alone. We now know that's not true, but explanations for the silence. For why? Despite the universe being old enough and large enough to have produced technological civilizations that should have been visible to us for millions of years, we haven't heard anything. The Great Filter hypothesis suggests that somewhere in the development from chemistry to intelligence to technology to interstellar expansion, there is a step or a series of steps that is extraordinarily difficult to pass, a filter, something that almost everything fails. If the filter is behind us, if the difficult step was abiogenesis, the origin of life from chemistry, or the development of eukaryotic cells, or the emergence of multicellular life, or the evolution of intelligence, then the news from the living world is the best possible news. It means we passed the hard part. The universe ahead is mostly empty of technological competitors, and humanity has a genuinely open future. But if the filter is ahead of us, if the difficult step is something that technological civilizations tend to fail at, something we haven't yet encountered, then the confirmation of life on a second world is, in a horrifying way, bad news, because it narrows the filter's location. Every data point of life elsewhere, particularly complex life, is evidence that the universe produces life and intelligence with relative ease, which makes the silence of advanced technological civilizations more ominous, not less. What kills civilizations? The candidates that researchers take seriously are varied: self-inflicted extinction through warfare, climate destabilization, or engineered pathogens; resource depletion that collapses technological infrastructure before interstellar capability is achieved; the development of technology, artificial intelligence, in particular, that transitions the civilization away from the kind of electromagnetic communication we're listening for, into modes we can't detect, or something stranger, something we haven't thought of yet, because whatever it is, has been uniformly effective at preventing any civilization from lasting long enough to become visible at interstellar scales. The living world, whatever it contains, whatever its biology has or hasn't produced in 6.8 billion years of evolution, is a data point in this calculation. And whether that data point is encouraging or terrifying depends on what the ship's instruments find when they look harder. Whether there is complexity, whether there is anything resembling multicellular structure, whether anything on that surface has in 6.8 billion years developed anything approaching a nervous system or something analogous to one on Earth, the news takes 1 year to arrive. And when it does, in the year 2126, the world it arrives into is not the world of 2026. 100 years have passed. The civilization that launched the mission has changed in ways that would be difficult to fully anticipate from the starting point of 2026, in the same way that the world of 2026 would have been difficult to fully anticipate from the world of 1926. But some things about human nature remain consistent across centuries. The need for meaning, the capacity for wonder, the impulse to look up, the hunger to understand what we are and where we came from, and whether anything else out there shares the experience of being alive in a universe that mostly isn't. When confirmation arrives that a probe deployed from a ship carrying the descendants of people who left Earth in 2026 has imaged the surface of a living world around another star, and that surface is covered in photosynthesizing organisms using a mechanism that convergently evolved independently from our own, the response on Earth is not one thing. It is not unified joy or unified terror or unified philosophical transformation. It is what human responses to extraordinary things always are: complex, contradictory, layered, deeply personal, and shaped by every individual's existing framework of meaning. Some people feel vindicated. Scientists who spent careers arguing for the prevalence of life in the universe, who faced skepticism and funding cuts and philosophical dismissal. Some feel existentially disoriented, people whose understanding of human uniqueness, in whatever form they held it, was quietly built on the assumption that we were the exception. Some feel a particular kind of grief for the people who died before this moment, for the grandparents who watched the launch in 2026 and didn't live to see the century-later payoff, for all the human beings throughout history who looked up at the stars and asked the question and died not knowing the answer, and some, perhaps more than any other response, because it is the most human, feel curiosity. A hunger that is not satisfied by confirmation but ignited by it, because one photosynthesizing surface covering on one world is not an answer. It is the opening sentence of an entirely new set of questions. What else is down there? Is there anything larger? Is there a marine biosphere in those oceans? Is there something anywhere in the history of that world that developed complexity comparable to animal life on Earth? And if not, why not? What was different? What path did that world's biology take over 6.8 billion years that led it to this abundant, successful, photosynthetically productive, and seemingly stuck at the microbial level? Here is the scientific context for why that last question matters so much. On Earth, life appeared relatively quickly after conditions became hospitable. Roughly 3.8 billion years ago, not long after the end of the late heavy bombardment period of intense asteroid and comet impacts. But for the first roughly 2 billion years of Earth's life history, essentially all life was microbial, single cells, simple prokaryotes, biochemically diverse, ecologically important. They transformed the atmosphere, built the oxygen we breathe, shaped the chemistry of the oceans, but structurally simple, not building toward complexity in any obvious directed way. The emergence of eukaryotic cells, cells with a nucleus, with internal organelles, with the cellular machinery required for the eventual development of multicellular life, appears to have happened approximately 1.5 to 2 billion years ago through an event called endosymbiosis. A larger cell engulfed a smaller one and, instead of digesting it, incorporated it as a permanent internal partner. The small cell became the mitochondrion, the energy-generating organelle found in virtually every complex cell on Earth. Without that specific event, the entire subsequent history of complex life, everything from algae to oak trees to octopuses to human beings, either doesn't happen or takes an entirely different and unknowable path. Was that event inevitable? Was it the kind of thing that happens reliably given enough time, or was it the biological equivalent of a lottery win, a specific contingent, low-probability event that happened to occur on Earth but might not happen elsewhere? If the living world's biology in 6.8 billion years has not produced anything resembling eukaryotic complexity, that tells us something profound about the probability of the endosymbiotic step, and therefore about the probability of complex, multicellular life anywhere in the universe. The universe might be full of microbial life and essentially empty of anything more complex. That hypothesis, sometimes called the rare Earth hypothesis, developed by paleontologist Peter Ward and astronomer Joe Kirschvink, suggests that simple life may be common, but the specific sequence of events required to produce complex multicellular life is extraordinarily rare. If the living world confirms this, if 6.8 billion years of biology produced only microbial complexity, it is simultaneously a confirmation that life is universal and a suggestion that intelligence is nearly unique. And then there is the question that the crew themselves have to live inside. Not as an abstract philosophical problem, as a daily reality. They are orbiting a living world. They have imaged its surface. They have detected its biosignatures. They have deployed one sterile probe that confirmed photosynthetic surface life, and now they have to decide every day, through months of orbital observation and remote study and heated internal debate, what comes next. The children of the fifth generation, the ones born in orbit around a living world under an orange star 1 light year from Earth, will be the sixth generation. The first human beings in history to grow up not under Earth's sun. The first human beings whose formative experience of sky and light and the shape of a solar system is not Earth's solar system at all. They will grow up looking out at that living world with the same relationship to it that Earth children have to their own planet as the sky of their childhood, the context of their early wonder. And if, eventually, a landing is made, if the contamination debate is resolved in favor of contact with whatever protocols can be developed, those sixth-generation children might be the first human beings to breathe alien air, to stand on alien ground, to feel the gravity of a world that has been alive for longer than our solar system has existed, under feet that belong to the great-great-great-grandchildren of people who left Earth in 2026. The distance is 1 light year, the time is 1 century, and the distance between who we were and who we become, between the species that launched and the species that arrives, is something that no unit of measurement in physics has yet been invented to describe. Wad's out. Not from the ship, not from the living world, not from the solar system we left behind or the one we spent a century traveling toward. Zoom out from all of it, from the entire scenario, from the century of travel and the generations of crew and the orange star and the photosynthesizing surface and the debates about contamination and the 23-year-old woman saying it's everywhere in a voice that carried the weight of 100 years of human effort and longing and sacrifice. Zoom out until 1 light year, the entire distance of this journey, the full span of everything we've discussed, the 100-year voyage of the most ambitious mission in human history, becomes what it actually is at the scale of the universe, a single step. barely a shuffle, a distance so negligible against the true size of the cosmos that calling it small is itself an overstatement. The Milky Way galaxy is approximately 100,000 light-years across. Our journey of 1 light-year, placed against that scale, covers 1/10,000th of the diameter of our own galaxy. If the Milky Way were the size of the continent of South America, roughly 8.5 million square kilometers, 1 light-year would be less than a kilometer, less than the distance from one end of a small town to the other. And the Milky Way is one galaxy, one of an estimated 2 trillion galaxies in the observable universe. 2 trillion, a number so large that if you counted one galaxy per second, without stopping, without sleeping, without pausing for a single moment, it would take you over 63,000 years to finish counting. The observable universe, the sphere of space whose light has had time to reach us since the Big Bang 13.8 billion years ago, stretches approximately 46 billion light-years in every direction from where we stand. The total volume of space it contains is incomprehensible in any direct sense. It can be written as a number, it cannot be felt. The human brain did not evolve to feel numbers like that. It evolved to track the movements of animals across a savanna, to read the weather in cloud formations, to recognize faces and remember paths through forests. The scales of cosmology are not something we were built for. We arrived at them through mathematics and instrumentation and centuries of careful, cumulative scientific work. And even then, even with all of that, we hold these numbers the way you hold a stone that is too large and too heavy, knowing you're gripping it but unable to truly lift it. But here is what I want you to understand. Here is the thing that cosmology, when it's working the way it should, delivers not as a deflating fact, but as something closer to a gift. The universe is not trying to humble you. The universe is not trying to make you feel small. The universe is not trying to do anything, because the universe doesn't have intentions. It doesn't have preferences. It doesn't care about human ambition or human grief or human wonder or the 100-year journey of a generation ship toward a living world 1 light-year away. And that indifference, that absolute, total, structural indifference, is precisely what makes the fact of us so extraordinary. In a universe that doesn't care, something happened. Chemistry assembled itself into self-replicating structures. Those structures competed and varied and accumulated complexity over billions of years. Complexity produced nervous systems produced consciousness produced curiosity, and curiosity produced beings who looked up at the vast, indifferent sky and instead of being crushed by it, asked, "What is that? How does it work? Are we alone in it?" And the most improbable question of all, can we go there? The universe didn't produce us on purpose, but it produced us, and we are, as far as we currently know, the only part of the universe that is aware of itself, the only arrangement of matter and energy that looks outward and inward simultaneously, that builds instruments to see farther than its own eyes can reach, that travels distances its body was never designed for, that grieves for the dead and hopes for the future of people not yet born. The atoms in your body were forged in the cores of stars that died before our sun was born. The calcium in your bones, the iron in your blood, the oxygen in every breath you take, none of it was made here. None of it originated on Earth. All of it was synthesized in the nuclear furnaces of stars, massive, ancient, long-dead suns that burned through their fuel, collapsed under their own gravity, and then exploded with enough energy to seed the surrounding space, with the elements that, billions of years later, assembled themselves into you. You are not on Earth. You are not visiting the cosmos. You are made of it. Every atom in your body has a history that stretches back 13.8 billion years through stellar nurseries and supernova explosions and interstellar clouds and the slow gravitational collapse that formed our solar system. You are not separate from the universe, looking at it through a window. You are the universe, temporarily organized into a shape that can look back at itself and feel something about what it sees. That is not a poetic flourish. That is a precise, scientifically accurate description of what you are. Now let's talk about what we actually know and don't know about the universe at the largest scales. Because this is where the story of 1 light year connects to something much larger, something that gives the entire journey a context that physics alone can't fully contain. The observable universe has a structure, not random, not uniform. On the very largest scales, scales of hundreds of millions of light years, matter in the universe is arranged in a pattern called the cosmic web. Galaxy filaments, vast threads of matter stretching hundreds of millions of light years, connect clusters of galaxies at their intersections, separated by enormous voids of nearly empty space. If you could see the universe at that scale, it would look like a three-dimensional foam, like the structure of a sponge, or the network of neurons in a brain, or the branching pattern of a lightning bolt. The resemblance to biological structures is striking enough that researchers have actually written papers comparing the statistical properties of the cosmic web to the network topology of neural connections in the human cerebral cortex. The comparison is not mystical. It reflects a deeper mathematical truth that certain network structures emerge from physical processes operating under similar constraint conditions, regardless of scale or substrate. The universe organizes itself into webs, so do brains, so do river systems, so do cities seen from orbit. There is a geometry to complexity, a set of shapes that nature returns to again and again across wildly different scales and physical contexts, and it is one of the most genuinely beautiful things that science has ever noticed. Within the cosmic web, our position is specific, mappable. Known our solar system sits in the Orion Arm, a minor spiral arm of the Milky Way, located roughly 26,000 light-years from the galactic center. We are not at the center of anything, not of our galaxy, not of our local group of galaxies, not of the observable universe, not of the cosmic web. We are in a relatively quiet suburban region of a fairly average spiral galaxy, what astronomers sometimes call the Goldilocks zone of the galaxy, not too close to the violent, radiation-drenched galactic center and its central supermassive black hole, Sagittarius A, with a mass of roughly 4 million times our Sun, and not so far out in the galactic hinterlands that the necessary heavy elements for complex chemistry are sparse. The Milky Way itself is part of a gravitationally bound collection of galaxies called the Local Group. The Local Group contains approximately 54 galaxies, dominated by two spirals, the Milky Way and the Andromeda Galaxy, also known as Messier 31. Andromeda is currently approaching us at roughly 110 kilometers per second. In approximately 4.5 billion years, the two galaxies will merge, not in a cataclysmic collision of individual stars, since the space between stars is so vast that direct stellar collisions are statistically improbable, but in a slow, gravitational dance that will stretch over hundreds of millions of years and ultimately produce a single, larger elliptical galaxy. Astronomers have already modeled this merger in extraordinary detail. The resulting galaxy has been informally named Milkomeda, and the Sun, if it still exists, which it barely will at that age, will almost certainly be in a completely different position relative to the galactic center than it occupies today. The Local Group is itself part of a larger structure called the Virgo supercluster, which is part of an even larger structure called Laniakea, a supercluster of galaxies stretching approximately 500 million light-years across, containing the mass of roughly 100 million billion suns. The name Laniakea comes from Hawaiian, meaning immeasurable heaven. It was identified and mapped in 2014 by a team led by astronomer Brent Tully at the University of Hawaii, using a new technique for mapping the gravitational flows of galaxies through space. We live in Laniakea, specifically in a quiet corner of a minor arm of one of its 200,000 member galaxies. And Laniakea itself is one of millions of superclusters in the observable universe, 1 light-year against all of that. But here is where I want to slow down and push back gently against the narrative that scale equals insignificance. Because that narrative, the one that says you are small, therefore you don't matter, is not a scientific conclusion. It's a philosophical error. And it's one that a lot of popular science communication makes without fully realizing it. Size is not the same thing as significance. Complexity is not proportional to volume. The most intricate, information-dense, causally consequential structures in the known universe are not the largest ones. They are biological ones. Specifically, they are neural ones. The human brain, roughly 1.5 kilograms of electrochemical tissue, contains approximately 86 billion neurons, each connected to thousands of others, forming a network of roughly 100 trillion synaptic connections. The information processing complexity of that network, operating in real time, is something that no supercomputer currently built can fully simulate. Not because we lack processing power, though we do, but because we don't yet fully understand the principles by which it works. The most complex known object in the universe fits inside your skull, and it is capable of modeling the universe around it, of building internal representations of stellar distances and galactic structures and quantum mechanics and evolutionary biology and the emotional texture of a century-long interstellar journey. The universe built something that can contain a model of itself. That is not a small thing. That is, cosmologically speaking, a staggering achievement. And there is another piece of physics that belongs in this conversation. Something that most people have heard of but few have truly sat with in the way it deserves, the fine-tuning of the universe. The fundamental constants of physics, the strength of gravity, the electromagnetic force, the strong and weak nuclear forces, the mass of the electron, the cosmological constant that governs the rate of expansion of the universe, are set at values that, if altered even slightly, would produce a universe in which no complexity of any kind is possible. A slightly stronger gravitational constant and the universe collapses back on itself before stars can form. A slightly weaker one and matter never coalesces at all, just a uniform, expanding gas with no structure, no stars, no chemistry, no life. A slightly different electromagnetic coupling constant and atoms don't form stable bonds, chemistry doesn't exist. Biology is impossible. The numbers are tuned, not by someone, not by intent, but as a brute observational fact, to values that permit complexity, that permit stars and planets and carbon chemistry and water and biology and brains and questions. Why? There are serious answers that physicists and cosmologists propose. The anthropic principle, the observation that we can only exist in a universe capable of producing us, so of course the universe we find ourselves in has the properties required for our existence. The multiverse hypothesis, the idea that there are an enormous or infinite number of universes with varying constants, and we necessarily inhabit one of the rare ones where the constants permit life. The simulation hypothesis, deeply speculative but taken seriously by some physicists, that the universe's fine-tuning reflects deliberate parameter selection by an external intelligence of some kind. None of these answers is satisfying in the way that most humans want their deepest questions answered. None of them provides closure. All of them open further questions. And that is exactly where science is most honest, not when it provides final answers, when it identifies the questions that are genuinely deeply hard, the questions that are not hard because we haven't tried. Hard because the answers, if they exist, may require ways of thinking that haven't been invented yet. Ways of thinking that might be sitting right now undeveloped in the mind of a child who has not yet been born. This is where the journey of 1 light-year becomes something more than a thought experiment about propulsion and generational psychology. It becomes a statement about what kind of species we are, about what we choose to reach for and why. Every civilization in human history has had a horizon, a physical boundary beyond which the world was unknown, and beyond which the bravest, most curious, most restless individuals went anyway, sometimes for resources, sometimes for power, sometimes for reasons that even they couldn't fully articulate. Something older than language, older than civilization, older than agriculture, a pull toward the unknown that seems to be written into the deepest operating instructions of our species. The ocean was a horizon. For tens of thousands of years, it was the ultimate boundary of the human world. Crossing it seemed impossible, then reckless, then heroic, then routine, then so ordinary that people do it in pressurized aluminum tubes while watching films and complaining about the food. Every impossible horizon, in retrospect, turns out to be a temporary limitation of technology and will rather than a permanent boundary of possibility. The atmosphere was a horizon. For all of human history, the sky was a ceiling, an impassable, untouchable boundary between the human world and the cosmic one. It was crossed for the first time with sustained powered flight in 1903. It was punctured for the first time with an orbital satellite in 1957. It was stepped through for the first time by a human being in 1961. Less than 60 years from first powered flight to human beings standing on the moon. 60 years. The interstellar medium is the next horizon, and we are, right now, in the position of someone standing on the coast in 1491, looking west across the Atlantic Ocean. We can see that there's something out there. We have instruments that detect it, measure it, characterize it from a distance. We know more about the nearest stars than any 15th century navigator knew about the Americas. But we haven't gone. Not in person. Not yet. The generation that goes, whenever they are, whatever century they belong to, will look back at us the way we look back at the first oceanic voyagers, with a mixture of admiration for the audacity, sympathy for the limitations, and a kind of tender gratitude for the fact that they tried, that they built the maps, that they pointed toward the horizon and said, "There!" There is one more thing I want to say in this part, something personal, something that I find myself returning to every time I sit with the scale of the universe and the smallness of 1 light-year against it. We are a young species. Anatomically, modern humans have existed for roughly 300,000 years. Civilization, in the sense of settled agriculture, cities, writing, accumulated transmitted knowledge for roughly 10,000. Science as a systematic, self-correcting method of understanding the natural world for roughly 400 years. Spaceflight for less than 70. The James Webb Space Telescope, which has given us the deepest and most detailed views of the universe ever captured, has been operational since 2022. It sees galaxies whose light left them over 13 billion years ago. It is detecting the atmospheric chemistry of planets orbiting other stars, and it has been running for less than 5 years. We are at the absolute beginning of this. Whatever we know now, however comprehensive and extraordinary the scientific picture of the universe feels from inside this particular moment in human history, is almost certainly going to look as preliminary to our descendants as medieval astronomy looks to us. We are the early chapters of a very long story, and the story is not about the universe learning to be understood. It's about us learning to ask better questions, questions that reach further, questions that are more honest about what we don't know, questions that treat the unknown not as a threat but as an invitation. 1 light-year in 2026. With everything we have, or will have, or might build in the decades of frantic, beautiful, frustrated, occasionally brilliant human effort between now and departure, It's not far enough. It never will be. That's the point. Tonight, go outside, if you can. If the sky is clear where you are, if the city lights aren't too thick, if there's even a small patch of dark overhead, go outside and look up. Not for long. You don't need to find anything specific. You don't need a telescope or an app or a star map. Just look up at whatever is there, the stars you can see, the darkness between them, the particular quality of silence that the night sky produces in a person who is paying attention to it rather than simply existing beneath it. I want you to try to hold two things in your mind at the same time. The first thing, every point of light you can see is a sun, not a decoration, not a symbol, a sun. A star, a nuclear furnace burning hydrogen into helium through gravitational compression, producing energy at a rate that makes every power source humanity has ever built look like a birthday candle. Many of those stars have planets. We know this now, not as a hypothesis, not as a philosophical preference, but as a confirmed observational fact established by thousands of detected exoplanets across the nearest few thousand light years of our galaxy. Planets are normal. Planets are what happens when stars form. The solar system is not the exception. It is, in its basic architecture, a fairly standard outcome of stellar formation physics. The second thing, you can't go there, not tonight, not in your lifetime, not in the lifetimes of your children or their children. The distance is real. The physics is honest. The nearest star to our Sun, Alpha Centauri, a binary system, is 4.24 light-years away. At 1% of the speed of light, it takes 424 years to reach. At the fastest speed any human-made object has ever traveled, the Parker Solar Probe, at its perihelion passage, reaching approximately 692,000 kilometers per hour. It would take over 6,000 years. Hold both of those things, the closeness of the cosmos, in the sense that it is everywhere and you are made of it, and the distance of the cosmos, in the sense that the physics of travel makes the stars unreachable on any timescale that a single human life can contain. Now ask yourself, how does that make you feel? I've asked that question, not literally, but in the form of this video, in the form of this entire thought experiment, for the last 9 parts. And I want to spend the final part not answering it for you, but sitting with you in the space where the answer lives. Because the answer is not the same for everyone, and whatever yours is, it tells you something true about yourself. Some people feel grief, a genuine, quiet grief for the places they'll never go and the things they'll never see. There is a word in Welsh, Hyriaeth, that describes a longing for something you can't return to, or a longing for something you've never had but feel the absence of anyway. The cosmos produces Hyriaeth in people who love it, a longing for the stars that is not quite sadness and not quite hope but something in between that doesn't have a clean name in most languages. Some people feel liberation. The scale of the universe, rather than crushing them, removes the weight of small concerns. When you have genuinely internalized the size of the observable universe, not just known it intellectually but felt it, the way you feel the cold of water when you swim in it, the ordinary anxieties of daily life lose some of their grip, not all of it. The anxieties come back, but for a moment, for the particular quality of moment that only the night sky and honest scale can produce, they recede, and what's left is something cleaner, a sense of proportion, a sense that the universe is very large and very old, and what happens here still matters, but matters in a way that is freed from the claustrophobic smallness of only thinking about here. Some people feel curiosity so intense it borders on physical sensation, an almost painful hunger to know what is out there, what the living world under the orange star actually looks like up close. What is oceans, whether anything has evolved complexity, whether the universe, across its 2 trillion galaxies and 13.8 billion years of stellar evolution, has produced minds other than ours that are looking back across the dark and asking the same questions. Whether the silence is loneliness or privacy, whether we are the first or the last, or simply one of an unimaginable number of conscious arrangements of matter, each isolated from the others by the brutal patience of distance. The journey we described, leaving Earth in 2026, traveling at 1% of the speed of light, arriving at 1 light-year after a century, is not a real mission. No one has built that ship. No one has solved the propulsion problem, the shielding problem, the food production problem, the psychological problem of generational confinement, the contamination problem, the deceleration problem. We are, right now, at the stage where the hardest parts are still theoretical, but theory precedes reality, always, without exception. Every technology that exists was, at some earlier point, a theory, an idea held in someone's mind before it existed in the world. The first person to imagine that fire could be controlled rather than feared. The first person to understand that falling objects follow a mathematical law. The first person to calculate that the Earth orbits the Sun rather than the other way around, in a century when saying so was dangerous. The first person to write down the equations that describe electromagnetic fields, who could not have imagined that those equations would eventually lead to the global communication network that delivered this video to you. Theory precedes reality. And the theory of interstellar travel, the careful, mathematically honest, scientifically rigorous study of what it would actually take to cross the distance between stars, is something that serious researchers are working on right now, at universities, at space agencies, at private organizations with names like the Breakthrough Starshot Initiative, which is developing the concept of laser-propelled light sails capable of reaching Alpha Centauri in approximately 20 years, not with human crew, but with gram-scale probes, tiny enough that the laser array required to push them to 20% of light speed is at least physically conceivable, if not yet buildable. 20% of light speed. For context, that is 60 million kilometers per hour. The fastest human-made objects ever built travel at less than 1% of that. But the physics permits it. The engineering is extraordinarily difficult. The cost is enormous. The technical challenges are genuinely formidable. And none of those things are fundamental barriers. They are engineering problems. They are resource problems. They are problems of the kind that human ingenuity, given sufficient time and motivation and accumulated scientific understanding, has a track record of solving. The question of interstellar travel is ultimately not a question about physics. The physics is hard but not prohibitive. It is a question about priorities, about what a civilization decides matters enough to pursue across generations, about whether the impulse to look beyond the current horizon, the impulse that has driven human exploration since before we had written language to record it, is something we continue to act on, or something we decide at some point is too expensive and too difficult and too far away to be worth the effort. Every generation that has made that second choice, that has looked at the horizon and said, "Not worth it," has been forgotten. Not entirely, but the ones who are remembered, the ones whose names and voyages and discoveries still carry weight across centuries, are the ones who looked at the horizon and said, "Let's find out what's on the other side." We are standing at one of those moments right now, not because we're ready to launch a crewed interstellar mission. We aren't, but because the tools we are currently building, the next generation of space telescopes, the advanced propulsion research programs, the emerging capability to detect and characterize the atmospheres of Earth-sized planets around other stars, the preliminary work on laser sail propulsion systems are the equivalent of the first shipbuilders learning to work with better timber. The voyage is not tomorrow, but the preparation is underway. And you are part of it, not metaphorically, Literally, every person who watches a video like this one, who reads a paper about exoplanet atmospheres, who looks up at the night sky and feels that particular mixture of awe and hunger and hireth, every one of those people is part of the cultural and intellectual ecosystem that makes scientific progress possible. Science does not happen in isolation. It happens in a civilization that values it, that funds it, that raises children who are curious enough to pursue it, that tells stories about it in ways that make it feel like what it actually is. The most important and most human thing we do. You, watching this, are part of that story, not as a passive audience, as a participant. The decisions your generation makes about what to prioritize, what to fund, what to celebrate, what to teach, will determine whether the mission we described in this video happens in 100 years, or 300 years, or never. Whether the generation that first looks at a living world under a foreign sun is 2 or 3 or 10 generations from now. Whether the silence of the interstellar medium is eventually broken, not by aliens broadcasting toward us, but by us, pushing carefully and determinedly outward, one impossible step at a time, 1 light year. At 1% of the speed of light, you leave Earth in 2026. You arrive, or your descendants arrive, approximately 100 years later. You travel 9.46 trillion kilometers through interstellar space, through the void between stars that is not truly void, that contains thin clouds of hydrogen and helium and complex organic molecules, and the dim, pervasive glow of the cosmic microwave background radiation, the afterglow of the Big Bang still faintly present everywhere in the universe, 13.8 billion years after the event that produced it. You travel through a space that is ancient and enormous and, by every measure we currently possess, indifferent to your presence. The cosmos does not know you are crossing it. The stars do not notice. The living world under the orange sun does not sense your approach. The universe does not hold its breath. And yet the crossing matters. Because you are part of the universe. Because the universe, in producing you, produced something capable of crossing it. Something that was made in stellar explosions and assembled over billions of years of biological evolution and shaped by 10,000 years of accumulated human knowledge and sent outward, not blindly, not randomly, not by instinct alone, but deliberately, consciously. With a map and a plan and a reason, the cosmos does not know you are there, but you know where you are. You know how far you've come. You know what it cost to get there and who paid the price and what they hoped you'd find. And you carry all of that. Every generation that lived and died in the dark between the stars. Every letter transmitted at light speed across increasing distances. Every child born under a foreign sun who has never known Earth except as a point of light. You carry all of it with you as you enter orbit around a world that has been alive for longer than our solar system existed. And when the surface resolves in the instruments, when the orange light catches the edges of a continent and an ocean, and something living and dense and everywhere across the coastal plains, when the young scientist on duty says those 4 words, it's everywhere. What she means, what those words contain, is not just a scientific observation. It's an answer to a question that every human being who has ever lived has carried somewhere inside them, in whatever form their culture and their language and their particular interior life gave it. The question beneath all other questions, the one that precedes religion and philosophy and science and art, the one that begins, for most of us, with a child lying on their back in the dark, looking up at a sky full of lights they don't yet have words for and feeling, not thinking, feeling that something enormous and mysterious is looking back. Are we alone? No, not in the universe, not in the dark, not in the asking. I want to end not with a conclusion but with an image, something small enough to hold, somewhere on Earth tonight, in a city with too much light pollution, in a rural field with a clear sky, In a suburb where the stars are faint but visible if you look carefully enough, someone is outside. Maybe they're a child, maybe they're very old, maybe they're somewhere in between. They're looking up at the same stars that every human being throughout all of history has looked up at, the same stars that prehistoric people named and navigated by, that ancient astronomers mapped with patient observation across a lifetime, that the first telescopes revealed as suns, that the first spectrographs revealed as furnaces of nuclear chemistry, that the first exoplanet surveys revealed as hosts of worlds. They're looking up at those stars and feeling something that they may or may not have words for. Something between wonder and longing and a quiet, steady sense that the universe is very large and they are very small, and somehow that is not a depressing thought but an extraordinary one. Somehow the smallness and the largeness are not opposites but a single feeling that doesn't have a name in any language yet invented. That feeling, whatever you call it, however it lives in you, is the beginning of every voyage humanity has ever made, every horizon ever crossed, every impossible thing ever built. It starts there, in the dark, looking up, feeling it, keep feeling it, keep looking up. The stars are not going anywhere, and neither, it turns out, are we. Thank you for spending this time in the dark with me. If this journey meant something to you, if it changed even slightly the way you see the sky tonight, then something real happened here. Something worth continuing. If you want to keep exploring the cosmos together, subscribe to the Cosmic Silence. New videos travel outward from here, deeper into the science, further into the mystery, always honest about what we know and what we don't. Hit the notification bell if you want to be the first to know when the next journey begins. And if you're ready to take your first real step toward the cosmos, not in a generation ship, but in your own backyard, tonight I want to tell you about something that genuinely changed the way I experience the night sky. The Celestron StarSense Explorer uses your smartphone's camera and a proprietary algorithm to map exactly where your telescope is pointed in real time, showing you what you're looking at and guiding you to objects you'd never find manually. No star charts, no frustrating setup, just point, look and understand. I've used it to find nebulae, star clusters, and the moons of Jupiter on nights where I had maybe 20 minutes of clear sky. The link is in the description. If you've ever wanted to start, this is the easiest starting point I've found. Until next time. The silence between the stars is not empty. We just haven't learned to hear it yet. And if this journey left you hungry for more, make sure to check out that video on the screen. It explores what a generation ship would experience on its way to Proxima Centauri, the closest star we'll ever try to reach. Click it. You're already in the right headspace. Don't waste it.